Tonight, somewhere in the constellation Serpens, 600 million light-years from where you are lying, a ring of stars is orbiting a golden core across a gulf of empty space. You cannot see it from here. The ring is a near-perfect circle of young blue stars. Between it and the core, the space is almost completely empty, a gap as wide as the distance from our Sun to the center of the Milky Way. The core is old and golden. No accepted mechanism in galaxy physics explains how those two things ended up at the same address. Tonight we will follow the collision theory until it breaks, and look through the gap itself, where something is waiting that no one expected to find there. In the summer of 1950, the work of mapping the sky was still largely done by hand. Photographic plates accumulated at observatories across the world. They were glass rectangles coated with light-sensitive emulsion, each one a frozen record of some small patch of sky from some specific night. Astronomers worked through these plates systematically, examining objects under magnification, measuring their brightness, sorting them into categories. Stars went in one column, galaxies went in another. And the soft, diffuse glowing shells left behind by dying stars went in a third. Arthur Allen Hoag was doing this kind of work when he found it. On one plate, in the constellation Serpens, there was a round, diffuse object with a bright central region and a faint outer structure. That combination of round shape, bright center, and faint outer halo matched what you would expect from a planetary nebula. The kind of object where a star in its final phase of life has expelled its outer layers, and those layers are now expanding slowly outward, glowing because the remnant stellar core is still hot enough to ionize the gas around it. Hoag noted the object and published a brief description in the 1950 volume of the Publications of the Astronomical Society of the Pacific, calling it a peculiar entity in Serpens and declining, carefully, to commit to a classification. The problem was not what the image showed. The problem was what happened when astronomers split the object's light through a spectrograph. When light passes through a prism or diffraction grating, it spreads into its component wavelengths, producing what astronomers call a spectrum. Every element in the universe absorbs and emits light at specific wavelengths fixed by atomic physics. Hydrogen produces lines at specific positions. Calcium produces lines at different positions. These positions are known precisely from laboratory measurements on Earth. So when you observe a spectrum from a distant object, you can compare where those lines actually appear to where they should appear if the source were stationary. If the object is moving away from you, the lines shift toward longer, redder wavelengths. Astronomers call this a redshift, and they express its magnitude as z, where larger z means faster recession, and, by the relationship between recession, velocity, and distance established by the expanding universe, greater distance from us. The spectral lines from Hoag's object were redshifted by a value of approximately z equals 0.045. That value translates to a recession velocity consistent with an object approximately 600 million light-years away, roughly 184 megaparsecs. To understand what that single measurement destroyed, you need to know the scale of planetary nebulae. The largest ones in our own galaxy span perhaps 5 or 6 light-years from edge to edge. At 600 million light-years, an object 5 light-years across would subtend an angle far below the resolution limit of any instrument that has ever existed. You would not detect it as a dim smudge. You would not detect it at all, at any wavelength, with any technology we have built or could plausibly build. A planetary nebula at that distance is not faint. It is nothing. Which meant what Hoag had found was a galaxy. A galaxy is a different matter entirely. Our own Milky Way spans somewhere around 100,000 light-years. Galaxies at 600 million light-years are entirely detectable, appearing as small, faint, extended objects in photographic surveys, which is exactly what this object was. But the shape was the issue. The planetary nebula hypothesis had been wrong about scale while pointing, in its visual logic, at something structurally real. The object really did resemble an expanding shell with a central concentration. It was not a shell. It was a ring of billions of stars orbiting a central core of other stars, with a band of nearly empty space between them. In 1950, that configuration had no name. Hubble worked out a classification scheme for galaxies in the 1920s that accommodated spirals, ellipticals, lenticulars, and irregulars, and it remains the foundation of galaxy morphology today. It had no category for a ring. The physical mechanism that could produce a galaxy-wide ring of stars had not been worked out in any detail. The Cartwheel Galaxy, now the most studied example of a collision-produced ring, existed in survey plates, but had not yet been understood in those terms. When you removed the planetary nebula hypothesis and were left with a ring-shaped galaxy, you were left with an object that the existing vocabulary of astronomy could not describe. We should be precise about what actually happened between Hoag's initial note in 1950 and any modern understanding of the object. It was not a single follow-up observation that resolved the classification. It was a slow accumulation of data over years and then decades. Better spectra arrived, then higher resolution imaging, then observations at multiple wavelengths. Each successive round added detail to an object that kept declining to fit the frameworks being applied to it. The ring became sharper, with better imaging. The age difference between the ring stars and the core stars emerged with spectral analysis. The absence of a nearby impactor galaxy registered gradually as the surrounding sky was mapped in greater and greater depth. What strikes me about Hoag's original paper is what it does not claim. His paper made no claim the data didn't support. He described what the plate showed, noted that the classification was uncertain, and left it there. The information that would eventually overturn his first hypothesis was not yet available, and he did not reach past what the data supported. That kind of patience with incomplete information is itself a form of precision. It kept the question honest, and the question stayed honest enough to remain open for 75 years. Every reassuring category that would have made this thing ordinary was removed by the same measurement that determined the distance. The object is a galaxy whose ring spans a distance comparable to the full width of the Milky Way, with a gap of empty space between that ring and its core wide enough to swallow our sun's entire neighborhood and leave nothing visible on either side. What remained after the redshift measurement, and what remains now, is a galaxy whose shape has no complete explanation. When the Hubble Space Telescope directed its advanced camera for surveys at Hoag's object in 2001, the image that came back was striking for reasons that go beyond the visual. What makes it scientifically significant is not the impression it creates, but what each feature represents physically, because each feature, properly understood, adds a new constraint to a problem that already had no easy solution. Begin with the outer ring. Its color is blue-white, luminous and sharp at the edges. That color is not incidental. The color of a star is a direct measure of its surface temperature, and surface temperature is a direct measure of mass and age. Blue-white stars burn at surface temperatures of roughly 20,000 to 50,000 degrees Celsius, several times hotter than our sun, which maintains a surface temperature of about 5,500 degrees Celsius. Stars this hot belong to spectral categories astronomers designate as O-type and B-type. They are the largest, most luminous, most energetic stars that form in any galaxy. They are also, by a large margin, the shortest-lived. An O-type star burns through its nuclear fuel in a few million years, roughly 1/500th of the current age of the universe. By the time a star with our sun's mass has consumed a fraction of its hydrogen, an O-type star has already exploded as a supernova and left a remnant behind. When you see a ring of blue-white stars, you are not seeing a permanent feature of a galaxy. You are seeing a snapshot of something recent. Star formation happened here, and it happened within the last few 100 million years at most. The central core presents a near-complete reversal. It glows warm yellow-orange, the color of G-type and K-type stars. Our Sun is a G-type star. These stars burn cooler, live longer, and form in quieter conditions than their blue counterparts. A G-type star has a lifespan measured in roughly 10 billion years. A K-type star lives even longer. The yellow-orange color of Hoag's core tells us that the dominant stellar population there is old. Not hundreds of millions of years old, but potentially several billion years old, formed when the universe was significantly younger and denser than it is now. You are looking at stellar populations separated by billions of years of cosmic time, orbiting within the same gravitational system. The ring carries the signature of a recent event. The core carries the signature of an ancient one. What the image does not show anywhere between them is a population of intermediate-age stars that would indicate a continuous process of galaxy formation connecting the two. A galaxy that grew and evolved in a single continuous history tends to distribute stellar ages throughout, older stars concentrated toward the center, younger stars scattered through the disk, with a gradual gradient rather than a sharp boundary. Hoag's object does not look like a single continuous process. It looks like two separate histories that ended up at the same address, with a band of dark space marking the border between them. The young ring stars require a trigger. Stars do not spontaneously arrange themselves in a ring configuration. Gas needs to be compressed simultaneously across a full circumference, reaching densities sufficient for gravitational collapse to produce new stars. That compression requires a cause, and the cause has to act consistently around the full ring rather than locally in one region. The image shows no obvious candidate for that cause. No second galaxy sits nearby at the same distance that could have served as an impactor. No asymmetry in the ring's brightness points to a direction from which energy arrived. No tidal disturbance is evident in the ring's shape. The young stars are there. Whatever triggered their formation left almost no other detectable trace. The gap between the ring and the core runs to approximately 25,000 light-years in width. Our Sun sits roughly 26,000 light-years from the center of the Milky Way, which means the gap inside Hoag's object is about as wide as that entire distance, a volume of space that, in our own galaxy, contains billions of stars, clouds of gas and dust, and portions of several spiral arms. In Hoag's gap, multi-wavelength observations find very little. Deep optical imaging detects very few stars. Radio observations at 21 centimeters, the wavelength at which cold neutral hydrogen gas is most directly detectable, find very low gas density. Infrared measurements show minimal dust emission. The gap is not just visually dark. It is dark across every frequency we have pointed at it, and the darkness is consistent with a genuine absence of ordinary matter rather than a region obscured by intervening material. The edges where the gap meets the ring and where the gap meets the core are notably sharp, a feature that persists across multiple imaging epochs and is difficult to produce in models of galaxy disruption, where material tends to spread and blur rather than maintain clean boundaries over hundreds of millions of years. The full system, including both the ring and the core, spans approximately 120,000 light-years in total outer diameter, comparable in size to the Milky Way. The core itself is roughly 17,000 light-years across. These are not small structures. Hoag's object is a galaxy of ordinary dimensions that has distributed nearly all of its visible mass into two structurally and temporally distinct zones, with a dark region nearly as wide as our Sun's distance to the galactic center separating them. The circularity of the ring is the feature that generates the most sustained scientific attention, and for good reason. Astronomers measure ring shape by comparing the maximum diameter of the ring to the diameter measured perpendicular to it. For a perfect circle, those measurements are equal, and the ellipticity equals 0. Hoag's ring approaches that value more closely than almost any other large-scale ring structure in the cataloged galaxy population. The ring is not approximately circular, it is very nearly exactly circular, and that precision is a physical constraint on how it formed. Producing a ring this symmetric from a collision between two galaxies requires an impact geometry that is extremely narrow, close to perfectly head-on, the impacting galaxy traveling almost exactly perpendicular to the disk plane. Simulations of ring galaxy formation produce near-circular rings only under a small fraction of possible initial conditions. And even then, the simulated rings typically show azimuthal brightness variations that Hoag's ring largely does not show. Each percentage point closer to a perfect circle places another requirement on the formation scenario. The ring is not getting easier to explain. It is getting more constrained with every measurement. One more detail in the 2001 image requires care. Visible through the dark gap, positioned between the outer ring and the golden core as seen from Earth, there is a faint structure that resolves, on close inspection, into another ring-shaped object. It is not part of Hoag's object. It is a separate galaxy at a much greater distance, aligned along the same line of sight by chance so that it appears framed within the gap. The two objects have no physical connection and no causal relationship. The alignment is a projection coincidence, the kind that occurs when you look through enough dark space and find something behind it. What the coincidence has prompted is a broader question. If we found this alignment by accident in one pointed observation, how many ring galaxies exist at greater distances that are being misclassified because they are viewed at unfavorable angles? The background galaxy tells us nothing about Hoag. It opens a question about how thoroughly we have counted systems like it. A near-perfect circle of young blue stars surrounding an ancient golden core, separated by a dark gap tens of thousands of light-years wide, with a second ring galaxy framed by chance behind it. Every detail narrows the range of possible explanations. A perfect shape tells us immediately what didn't happen here, even before we understand what did. Most of what fills the interior of a galaxy cannot be seen by looking at it. Visible stars account for a small fraction of the total mass. The rest is distributed as cold gas, warm gas, hot plasma, magnetic fields, and dark matter, each component occupying the same volume as the stars, but invisible to any instrument that only records optical light. Cold neutral hydrogen emits at radio wavelengths. Dust emits in the far infrared. Hot ionized plasma emits in X-ray. A complete picture of what a galaxy contains requires looking across the entire electromagnetic spectrum, because each frequency carries a different kind of matter into view. Astronomers have pointed all of these instruments at the gap inside Hoag's object. The answer came back the same from each one. Optical imaging at the deepest available sensitivities shows very few stars in the gap. That much is visible in any photograph of the system. But photographs in optical light can miss cold gas, can miss dust too faint to scatter visible wavelengths, and can miss stellar populations too dim to register above the noise floor. So optical silence is one data point, not a conclusion. Radio observations at 21 centimeters reveal neutral hydrogen gas by detecting the specific wavelength emitted when a hydrogen atom's electron flips its spin. This is how astronomers map the cold gas supply of galaxies, the raw material from which new stars form. Neutral hydrogen emission traces the invisible architecture of galactic disks, often extending far beyond the visible stellar boundaries. In Hoag's gap, the neutral hydrogen signal is very low. The cold gas that would normally occupy the interior of a galaxy at this scale, and that would be detectable at this technique's sensitivity, is largely absent from the region between the ring and the core. Infrared observations track dust, which absorbs starlight and re-emits it at longer wavelengths as heat. Dust in galaxies is not uniformly distributed, but it tends to follow the gas closely, and where there is enough gas for star formation, there is almost always enough dust to produce an infrared signal. In the gap of Hoag's object, far infrared emission is minimal. The dust that should accompany whatever gas remains is either genuinely absent or present at levels below what current instrumentation can resolve at 600 million light-years. X-ray observations probe a different regime entirely. Hot plasma, heated to millions of degrees by supernova remnants, stellar winds, or accretion processes, emits X-rays. Galaxies with significant star formation produce X-ray halos from this hot gas phase. The gap in Hoag's object shows no significant extended X-ray emission. 4 instruments, 4 different physical processes, 4 different ways of detecting matter in the universe. Each one returns the same answer from the same region of space. This kind of convergent silence across unrelated frequencies is not noise or observational artifact. It is a measurement. The gap is not hiding something in a wavelength we haven't checked. It is telling us, through every available channel, that the ordinary matter that should be filling that volume is not there. Physicists have a term for the threshold at which gas can collapse under its own gravity to form stars, the Jeans criterion. Below a certain gas density, thermal pressure and random motions prevent gravitational collapse, and star formation cannot proceed regardless of how long you wait. The gas in Hoag's gap appears to be below this threshold, either because there is so little of it that the density never reaches what collapse requires, or because whatever gas remains is heated and disturbed enough to stay above the collapse temperature. Either way, the gap is not simply a place where stars haven't formed yet. It is a place where the conditions for star formation are not currently present and, based on current observations, may not have been present for a very long time. Something moved the material. Not just reduced it or thinned it out, but moved it out of a region roughly 25,000 light-years wide, comparable to the distance between our Sun and the center of the Milky Way, and maintained that evacuation long enough for the edges to become the sharp boundaries we observe today. Because the edges are where this problem becomes genuinely strange. A disruption event in a galaxy does not produce sharp edges. When galaxies collide or when internal dynamics redistribute material, the result is gradual density gradients, streams of stars and gas bleeding into adjacent regions, tidal features that blur across thousands of light-years. The Cartwheel Galaxy, which is the most studied case of collision-produced ring structure, shows exactly this kind of messiness. A ring with brightness variations, streams of material between the ring and core, a detectable impactor galaxy, signs of ongoing redistribution everywhere you look. Hoag's gap, by contrast, presents a clean inner boundary where the ring meets empty space, and a clean outer boundary where the empty space meets the core. The gradients are steep, the borders hold. Sharp edges in physical systems require ongoing maintenance. A river's bank stays sharp because water is continuously cutting into the soil and carrying it away. A smoke ring holds its shape because it is spinning. A pressure boundary in a fluid holds as long as the pressure difference on each side is sustained. Edges that are simply left behind by past events don't stay sharp, they spread. Diffusion, differential rotation, gravitational perturbation, thermal pressure. Any of these processes will blur a sharp edge over the timescales involved here, which are measured in hundreds of millions of years. That Hoag's gap edges remain sharp means something is either maintaining them against those blurring forces, or the gap formed far more recently than the ring's oldest stars would suggest, which would require a different trigger story than any currently proposed. There is one component of matter that is almost certainly present in the gap regardless of what the optical, radio, infrared, and X-ray data show. Dark matter does not follow baryonic matter. It does not collect into stars or gas, clouds, or dust grains. It distributes through gravitational structures according to its own dynamics, which are governed almost entirely by gravity at large scales and are largely independent of the density of ordinary matter. The dark matter halo of Hoag's object almost certainly extends through the gap at some density. The gap is a void in luminous matter, not necessarily in total matter, but we cannot observe dark matter directly. We infer its presence from its gravitational effects on visible material, and at Hoag's distance and at the spatial resolution required to map density across the gap, those inferences are not yet precise enough to tell us whether the dark matter distribution inside the gap differs from what surrounds it. What we can say is this: The gap in Hoag's object is not the passive result of material being distributed elsewhere. Passive redistribution leaves gradients. This leaves edges. The question is not only what created the gap, but what prevents ordinary matter from settling back into it. That is a different question, a harder one, and it points towards something actively shaping the interior of this galaxy, rather than a single past event whose effects are fading with time. Something evacuated 25,000 light-years of galactic interior, maintained clean boundaries on both sides for long enough that we observe them as sharp today, and left no detectable gas, dust, or plasma in the volume behind it. Whatever it was, it has been thorough. Light carries a clock inside it. The color of a star is a direct consequence of its surface temperature. Its surface temperature is a direct consequence of its mass. Its mass determines how fast it consumes its nuclear fuel, and the rate of fuel consumption determines the star's lifespan with a precision that makes stellar lifetimes one of the most reliably calculated quantities in all of astrophysics. A star twice as massive as our Sun lives roughly 1/4 as long. A star 10 times as massive lives roughly 1/100th as long. The relationship between mass and lifespan is steep and well-constrained, which means that when you look at the color distribution of an entire stellar population, you are not just seeing what colors happen to be present. You are reading the age of the system. The blue-white end of the spectrum belongs to stars that burn hot and fast and cannot exist for long. Every blue-white star you detect is a star that formed recently enough not to have died yet. Astronomers make this quantitative through a technique called isochrone fitting. When you plot the luminosities and temperatures of a large sample of stars from the same population on a diagram, the pattern they form traces an evolutionary track. Theoretical models of stellar evolution predict what that track should look like for populations of different ages. The oldest stars in any given population have consumed their fuel and migrated away from the main track first, and the point at which the population's stars begin leaving that track tells you how old the oldest surviving members are. Applied to a stellar population at Hoag's distance, this method carries real uncertainties, but it produces constrained estimates rather than guesses. The ring's population is consistent with an age of tens to at most a few 100 million years. The core's population is consistent with an age of several billion years, potentially as old as 5 to 10 billion years. Sit with the difference those numbers represent. The universe itself is approximately 13.8 billion years old. The core of Hoag's object may contain stars that formed when the universe was less than half its current age, when the cosmos was denser and hotter and galaxy formation was proceeding at a rate that has since slowed substantially. The ring, by contrast, contains stars that formed after complex life had already been evolving on Earth for hundreds of millions of years, after the dinosaurs had already appeared and gone, in some estimates after the first ancestors of our own genus had already walked upright. These two stellar populations are not slightly offset from each other in time. They are separated by an interval that contains most of the history of complex life on Earth. Normal galaxy formation does not produce this. A galaxy that assembles and evolves in a single continuous history distributes stellar ages throughout its structure. The oldest stars concentrate toward the center, where material collapsed first under gravity. Younger stars scatter through the disk, formed later as gas continued to accrete, and as density waves in the spiral arms compressed material into new generations of stars. The age gradient is present, but it is a gradient, not a gap. You can find stars of intermediate age between the oldest core stars and the youngest disk stars because the formation process was continuous and distributed. Hoag's object does not have this gradient. What it has is two distinct populations separated by billions of years of cosmic time, with a corresponding gap in physical space between them, and almost nothing in between. Deep spectroscopic imaging of the gap region, looking for the specific spectral signatures that would indicate stars of intermediate age, finds very little. The population is bimodal in a way that the standard picture of galaxy evolution does not naturally produce. Either the ring and the core have completely separate formation histories, or a single event produced an age discontinuity so clean that no intermediate population formed anywhere between them. Both options require explanation, and neither has one. The ring's star formation was not spontaneous. Stars do not arrange themselves in a perfect circumference around a galactic center without a cause. Gas has to be compressed, simultaneously, across tens of thousands of light-years, to densities sufficient for gravitational collapse. That requires a trigger, an external or internal event that pushes material through the threshold for star formation at the same time around the full ring. The trigger left its signature in the ring's young stellar population. It left almost no other detectable signature anywhere in the system. If the trigger was a collision, then the collision was energetic enough to reorganize stellar material across 120,000 light-years of circumference and trigger new star formation across that entire span. Simultaneously, an event at that energy scale, passing through or near the center of the system, should have left traces on the core, disturbed kinematics, where the core stars show elevated velocity dispersions from the gravitational shock, possibly a burst of star formation in the core itself as the impacting body passed through and compressed the central gas supply. Or at minimum, some asymmetry in the core's structure, some departure from the smooth, undisturbed elliptical shape it presents in every observation. The core shows essentially none of these things. It is old, smooth, quiet, and dynamically cold, the signature of a system that has not been significantly disturbed in a very long time. The collision scenario needs the impacting galaxy to have been energetic enough to produce Hoag's ring and invisible enough to have left the core untouched. Those two requirements push in opposite directions. A high-energy impact disturbs what it passes through. A low-energy impact does not produce a ring of this scale. There is no obvious place in the parameter space of collision physics where an impactor produces exactly the ring we observe while producing exactly the non-disturbance of the core we observe. The standard collision picture needs the energy to flow into the ring and around the core simultaneously, which requires a very specific and narrow impact geometry that simulations have not yet reliably reproduced. 2 billion years of age, separating a blue ring from a golden core, with a clean spatial gap between them and an undisturbed core that saw none of the violence the ring apparently experienced. You can read those facts as a paradox to be resolved, or you can read them as a constraint. Whatever happened here was not a standard galaxy formation event. It was something specific. Something whose effects were precise enough to reorganize tens of thousands of light-years of stellar material while leaving an adjacent region of the same system in a state of deep, undisturbed quiet. That kind of precision is not what disruption events normally produce. Disruption events are messy by nature. Hoag's object is not messy. And that, more than any other single feature, is the thing that keeps resisting explanation. Nearly every large galaxy in the observable universe harbors a supermassive black hole at its center. This is not a hypothesis anymore. It is one of the more robust findings in extragalactic astronomy from the last 3 decades, established through detailed kinematic observations of stars and gas moving near galactic centers at velocities that cannot be explained by the visible matter alone. The evidence for supermassive black holes in galactic nuclei is now so consistent across so many different galaxy types and so many different observation techniques that their absence in a large galactic system would be the more surprising finding. Hoag's object has a center. The question is what it contains, how massive it is, and whether it is doing anything. Astronomers established a relationship between supermassive black holes and their host galaxies that is one of the more remarkable regularities in all of astrophysics. The mass of the central black hole in a galaxy correlates tightly with the velocity dispersion of the stars in the surrounding bulge, the characteristic spread of stellar velocities measured through the Doppler broadening of spectral lines. Larger bulge, faster stellar motions, more massive black hole. The relationship, called the M-sigma relation, holds across black holes spanning 5 orders of magnitude in mass, from millions to tens of billions of solar masses, in galaxies spanning an enormous range of sizes and morphologies. Its existence implies that black holes and their host galaxies grew together, each regulating the other's development through a feedback process that operated over billions of years. Applied to Hoag's core, which has a stellar velocity dispersion and a bulge luminosity consistent with a substantial elliptical-type system, the M-sigma relation predicts a black hole mass somewhere in the range of tens to hundreds of millions of solar masses. This estimate carries real uncertainty because Hoag's distance makes precise velocity dispersion measurements difficult, and the relation itself has scatter. But the prediction is not vague. It says that at the geometric center of that smooth golden core, within a region perhaps a few light-years across, there is almost certainly an object with a mass equal to tens of millions of suns compressed into a volume smaller than the distance between our own sun and its nearest stellar neighbor. And it is not making a sound. No broad emission lines in the spectrum of the core, which would indicate gas heated to tens of thousands of degrees by an accretion disk around an active black hole. No hard X-ray point source at the nucleus, which would indicate high-energy radiation from material falling into a compact object. No radio jets, which many active galactic nuclei produce when their central engines are consuming material at high rates. The core of Hoag's object is, at every observed wavelength, consistent with a galaxy whose central engine has shut down completely. Quiescence in a black hole is not death. Black holes do not cease to exist when they stop accreting. They sit unchanged because nothing about a black hole changes unless material crosses the event horizon. What changes is the supply of material available to cross it. A black hole that has consumed the gas in its immediate vicinity has no accretion disk, no jets, no emission. It is present at full mass with zero output. Astronomers describe this state as starved, which is a more precise word than it first sounds. The engine exists at full capacity, but the fuel is gone. Our own galaxy's central black hole, Sagittarius A, with a mass of approximately 4 million solar masses, is in this state right now. It is there, measurable by the orbits of stars around it, and it is consuming almost nothing. The spectroscopic signature of Hoag's core carries information about how that starvation happened. Buried in the core's spectrum are absorption features from hydrogen's Balmer series. The strength of these features relative to other lines in the spectrum is diagnostic. Strong Balmer absorption without corresponding emission lines is the spectroscopic fingerprint of a stellar population that contains a significant number of relatively young A-type stars. The emission lines that active star formation would produce are absent because the starburst is over. The A-type stars that the starburst left behind are still present, readable in the spectrum, but aging toward the red end. Galaxies with this signature are called post-starburst systems, and what they tell you is that the host galaxy experienced a major episode of star formation that then terminated abruptly, exhausting or expelling the gas supply before the process could continue. Hoag's core may carry this signature. The spectral data is not clean enough at Hoag's distance to make a definitive diagnosis, and researchers who have examined it have noted the resemblance to post-starburst features while stopping short of a firm classification. But if the resemblance is real, it means the core has its own history of violence that is now entirely over. It formed stars, possibly in a burst, and then went quiet. The black hole at its center fed during that episode, then starved when the gas was exhausted. What we observe today is the aftermath, an old, smooth, dynamically settled core with a dormant black hole at its center and a spectral residue of a star-forming event that ended billions of years ago. Consider what this implies for the gap. When a supermassive black hole is actively accreting at high rates, the energy it releases is not contained locally. A fraction of the gravitational energy released as material falls inward escapes as radiation, jets, and high-velocity winds. These outflows can couple to the gas in the surrounding galaxy at distances of tens of thousands of light-years, heating it, dispersing it, and preventing it from cooling back into the dense molecular clouds that star formation requires. This is the mechanism astronomers call AGN feedback, and it is invoked to explain why the most massive galaxies in the universe tend to have suppressed or halted star formation, while their less massive neighbors continue forming stars. The black hole at the center acts as a regulator, and when it is active, its regulation reaches across scales that dwarf the black hole itself by factors of millions. The gap in Hoag's object spans roughly 25,000 light-years. AGN feedback in massive galaxies can operate across comparable and larger scales. The question that has not been satisfactorily answered is whether the gap is an aftermath of a collision that evacuated the region, or whether it is an aftermath of the core's own black hole, which may have fired its engine during the core's ancient starburst episode and swept the interior of the galaxy clean before going quiet. If the latter, the sequence would look like this. The core formed first. Its black hole became active during the starburst. The AGN output dispersed the interior gas over a period of hundreds of millions of years. The dispersed gas eventually settled into the outer regions of the system and triggered the ring's star formation, and the black hole then starved as the interior was emptied. The ring would be the black hole's exhaust. The gap would be the channel it carved. This scenario has not been confirmed. It faces its own difficulties. The geometry of AGN outflows does not naturally produce perfect rings of star formation at large radii, and the detailed energetics would need careful modeling against the observed ring mass and star formation rate. But it is not ruled out by current data either, and it has one significant advantage over the standard collision picture. It does not require a missing impactor galaxy. Because there is no impactor, the agent is already in the system, sitting at the center, silent, with its history of activity buried in the spectral residue of an ancient starburst. Somewhere at the center of Hoag's core, within a volume a fraction of a light-year across, there is almost certainly an object more massive than tens of millions of suns. We have not imaged it. We have not confirmed its mass precisely. We have inferred its likely existence from the stars orbiting around it and from a relationship between black holes and their host galaxies that has held across thousands of observed systems. The most massive object in Hoag's object may be the one leaving the least evidence of its presence, and its past behavior during an episode of activity we can no longer directly observe may have shaped everything we can see. Drop a stone into still water and watch what happens at the surface. The impact point becomes the origin of a circular wave that expands outward at a speed determined by the medium's properties. The wave does not carry the water with it. It carries energy through the water, compressing the surface as it passes, then releasing it. The pattern that results is the signature of an impulsive force applied at a single point to a medium capable of transmitting that impulse outward uniformly in all directions. Scale that process up by a factor of roughly 1, followed by 18 zeros, and you have the leading explanation for how ring galaxies form. A smaller galaxy falls toward a larger one at high velocity. If the angle of approach is close to perpendicular to the larger galaxy's disk, and if it passes close enough to the galactic center, the gravitational perturbation it produces propagates outward through the disk as a density wave, compressing gas as it expands. Gas that is compressed past the gene's threshold collapses under its own gravity and forms stars. If the compression is sufficiently symmetric, the stars that form trace a ring around the impact center. The wave continues outward. The ring expands, and the impacting galaxy continues through and beyond the disk, now moving away in the direction it was already traveling, somewhat disrupted but still present somewhere in the surrounding volume. This mechanism is not theoretical speculation. It has been observed directly. The Cartwheel Galaxy, approximately 500 million light-years away in the constellation Sculptor, is the most completely documented case. Its outer ring is bright and unambiguous, And the most important thing about the cartwheel image is not the ring. It is what sits approximately 250,000 light-years away from the cartwheel's center in the same image, a smaller galaxy, misshapen and disturbed, trailing faint connective structure back toward the ring system it passed through. The aftermath of the cartwheel collision is legible. You can point to the impactor. You can trace the tidal streams. You can see where the energy went and where the impactor went afterward. The evidence is still there because the collision was recent enough that dispersal has not yet erased it. Applied to Hoag's object, the collision model makes specific predictions. Each prediction is a piece of evidence that should be present and detectable if a collision caused what we see. Prediction 1. The impactor should be nearby, at typical galactic encounter velocities of several hundred kilometers per second, and given the estimated age of Hoag's ring stars at tens to a few hundred million years, the impactor has had that same interval of time to travel from the point of impact. At 300 kilometers per second over 100 million years, it would have traveled roughly 30,000 light-years, well within any survey of the region around Hoag's object. Deep imaging of the surrounding field at Hoag's distance has found no obvious candidate at the right distance with the right properties. The search has not been exhaustive, and a sufficiently small or diffuse impactor could fall below current detection limits. But a galaxy massive enough to produce Hoag's ring should not be a whisper in the data. It should be visible. Prediction 2. There should be tidal features. When two galaxies interact gravitationally, they pull material out of each other. Stars and gas from both systems stretch into elongated streams along the direction of the encounter, producing tidal tails and bridges that can extend for hundreds of thousands of light-years and persist for hundreds of millions of years before dispersal. The cartwheel system shows these structures. Hoag's object, in deep imaging at multiple wavelengths, does not show obvious tidal structures connecting the ring or core to any surrounding material. The system appears isolated. Its edges are clean. Material that should have been pulled out of position during a collision is either absent or below current detection thresholds. Prediction 3. The ring should be asymmetric. The density wave model produces a ring most efficiently when the impact is exactly head-on, perfectly perpendicular, perfectly centered. Any deviation from this ideal geometry produces a ring that is brighter on the side closest to the impactor's entry point, or elongated along the direction of impact, or irregular in a way that encodes the geometry of the encounter. Real collision ring galaxies almost always show these asymmetries. Simulations of the mechanism confirm that perfect symmetry requires initial conditions so constrained that they represent a tiny fraction of all possible collision geometries. Hoag's ring is among the most circular and symmetric structures ever measured in a large galactic system. Its ellipticity is very close to zero. Either the impact geometry was extraordinarily precise, or Hoag's ring did not form from a collision at all. Prediction 4. The core should show disturbance. An impacting galaxy passing through or near the center of a larger system does not leave the center untouched. Gravitational shocks propagate inward as well as outward. The central stellar population should show elevated velocity dispersion. The core might show morphological disturbance, an off-center nucleus, or structural asymmetry. There might be evidence of star formation in the core triggered by the compression of central gas during the impact passage. Hoag's core is old, smooth, dynamically settled, and spectrally consistent with a stellar population that has not been significantly disturbed in billions of years. Whatever happened to produce the ring, the core does not appear to have noticed. 4 predictions, 4 absences. This is the structure of a problem that does not resolve cleanly in either direction. The ring of young blue stars is exactly what the collision model predicts. The absence of its supporting evidence is exactly what a system that never had a collision would produce. Hoag's object offers the fingerprint of a collision and refuses to offer the body. There is a version of the collision model that can accommodate each individual absence. The impactor could have been small enough and diffuse enough to be absorbed completely into the core, leaving no visible remnant. The tidal features could have dispersed below detection thresholds over the elapsed time. The asymmetries could have been smoothed by subsequent orbital dynamics. The core could have been less affected than typical because the impact was extremely precisely centered. Each of these explanations is separately plausible. The problem is requiring all of them simultaneously. Each accommodation narrows the parameter space of the original impact scenario further, requiring a smaller impactor, a more precisely centered trajectory, a longer elapsed time since impact, and a more unusual subsequent evolution. At some point, the number of specific conditions required to rescue the hypothesis from each failing prediction exceeds what probabilistic reasoning allows us to call an explanation. The model becomes a list of rescue clauses rather than a mechanism. The deepest version of this problem is not the missing impactor or the absent tidal streams, it is the circularity. When researchers run simulations of head-on galactic collisions specifically attempting to reproduce Hoag's ring, the parameter space that produces near-zero ellipticity is narrow. Getting the ring's circularity right means the impact angle must be close to perpendicular within a very small tolerance. Getting the gap's emptiness right means the impact energy must be distributed outward very efficiently. Getting the core's undisturbed state right means the impact must have missed the center or passed through it in a way that transferred minimal energy inward. These three requirements impose simultaneous constraints that simulations have not yet satisfied in a single run. Any set of initial conditions that produces the right ring tends to produce the wrong core, or the wrong gap, or the wrong circularity. The model that works for the cartwheel does not converge on Hoag's object. 75 years ago, a round smudge on a photographic plate turned out to be a galaxy. The most natural explanation for a galaxy with a ring formed from young stars points toward a collision. The collision model makes specific predictions. The predictions are largely absent. The mechanism that explains most ring galaxies does not, in any simulation so far published, explain this one fully. What makes this more than an unsolved puzzle is what the absences imply. Evidence that isn't there is still evidence. Its absence in a system this well observed, across this many observational approaches, over this many decades, is not a gap in the data. It is the data. The collision left no body, no tidal streams, no asymmetric ring, no disturbed core. Either it happened under conditions so specific they border on implausible, or the ring formed another way entirely. And if it formed another way, that way has not yet been named. Forensic reasoning in astronomy works the same way it works in any other investigation. You infer the properties of a cause from the properties of its effect. When a galaxy interaction produces a ring, the ring encodes information about what produced it. The mass of the impacting galaxy determines the energy of the density wave. The energy of the wave determines the scale of the ring, the velocity at which it expands, and the mass of stars that can form within it. Working backward from Hoag's ring, you can calculate what the impactor needed to weigh, how fast it needed to be traveling, and how recently the encounter had to have occurred. Each of those values places the missing impactor somewhere specific, in a particular mass range, in a particular region of the sky, within a particular distance from Hoag's center. This is not a vague search. It is a constrained one. Velocity and time constrain the impactor's location tightly. Ring-producing galaxy encounters occur at speeds of several hundred kilometers per second, typical of galaxies interacting within a cluster or group environment. Hoag's ring stars are young. Their blue-white color and spectroscopic properties place them at tens to at most a few 100 million years old. If the collision happened 100 million years ago, an impactor traveling at 300 kilometers per second would have covered approximately 100,000 light-years from the point of impact, roughly the same as the distance between our Sun and the far edge of the Milky Way. If the ring is 200 million years old and the impactor moved faster, the distance grows to several 100,000 light-years at most. Either way, it should still be in the immediate galactic neighborhood of Hoag's object, well within the volume that any deep photometric survey covers when it images that region of sky. The cartwheel system shows us exactly what a detectable impactor looks like. The galaxy that punched through the cartwheel sits approximately 250,000 light-years from the ring center, visually misshapen and elongated by the tidal forces of the encounter, trailing a faint bridge of disturbed material back in the direction it came from. Its distance matches the cartwheel's distance. Its spectral properties are consistent with having undergone a gravitational interaction. It is not subtle. At the cartwheel's distance, comparable to Hoag's object's 600 million light-years, a galaxy of that mass and luminosity appears clearly in deep imaging. You can point to it without ambiguity, measure its redshift, confirm the match, and consider the impactor identified. Around Hoag's object, that object does not appear. Deep, wide-field imaging of the surrounding volume shows background galaxies at various distances and the occasional foreground star, but no obvious candidate at Hoag's redshift with the size, luminosity, and disturbed morphology expected of a post-collision impactor at the right distance. The search has been conducted across multiple imaging datasets over multiple decades. No confirmed candidate has emerged. The first escape route offered to the missing impactor is absorption. Perhaps the impacting galaxy was small enough and moving fast enough that after passing through Hoag's disk, it fell back under the gravitational attraction of the system, decelerated, and was disrupted and absorbed into Hoag's core over the subsequent millions of years. A sufficiently small satellite galaxy, tidally stripped and dissolved, would leave no distinct remnant. The stars it carried would mix into the core's existing population. Its gas would be incorporated or heated and dispersed, and nothing obviously foreign would remain to identify. If the impactor was absorbed, it is not hiding somewhere in the surrounding sky. It is already inside the system we are looking at. Producing a ring at Hoag's scale requires a minimum impactor mass that can be estimated from the ring's properties. The ring spans roughly 120,000 light-years in outer diameter. The density wave that produced it had to compress gas across that entire circumference with enough energy to trigger star formation across a coherent ring rather than locally in one region. The mass contained in the ring's stellar population alone provides a lower bound on the gas mass the density wave needed to sweep up, and the gas mass provides a lower bound on the energy the impactor needed to inject. Working through the numbers, the impactor needed a mass of at least several billion solar masses, possibly tens of billions, to have produced a density wave energetic enough to do the job at this scale. A galaxy of tens of billions of solar masses does not merge with another galaxy's core without leaving visible signatures. Galaxy mergers of comparable mass ratios produce structural disturbances that persist for billions of years after the event. The core develops an off-center nucleus, or elevated velocity dispersion, or stellar shells, or excess light in the outer regions from disrupted stars deposited during the merger. These signatures have been catalogued in hundreds of observed post-merger systems. Hoag's core shows essentially none of them. It is smooth, centered, dynamically cold, and structurally unremarkable for a core of its age. If a galaxy of the required mass merged into it within the last few 100 million years, the core has recovered so completely that no instrument yet applied has found any trace of the event. That level of recovery, on that timescale, would itself require explanation. A second possibility is that the impactor exists in the surrounding volume but has faded below the detection threshold of current surveys. Galaxies can lose their gas through ram pressure stripping from intergalactic medium, or through internal feedback from star formation and AGN activity, becoming extremely diffuse systems of mostly old, low-luminosity stars. Such galaxies can have the total mass of a moderate-sized galaxy spread over an area so large that their surface brightness falls below what photometric surveys easily detect. Perhaps Hoag's impactor became one of these after the encounter. Stripped, disrupted, extended into near invisibility by tidal forces during the passage, now glowing at surface brightnesses too low for any published survey to have registered it. Ring formation constrains this possibility as well. An ultra-diffuse galaxy, extended across tens of thousands of light-years with a shallow density profile, does not interact with a target galaxy's disk the way a compact, concentrated impactor does. The density wave mechanism depends on the impactor's gravitational influence being applied locally and impulsively. A diffuse system spread over a large volume applies its gravitational influence more gradually and over a larger area, producing a weaker, broader, less coherent wave. Simulations of ring formation using diffuse impactors produce rings that are wider, fainter, and less sharply defined than what Hoag's object shows. The very properties that would make Hoag's impactor invisible to current surveys also make it a poor candidate for producing the ring we observe. 3 hiding places, 3 closures. The impactor cannot be far away because the ring's age places it within a surveyable volume. It cannot have been absorbed without leaving detectable core disturbances because the mass required to produce the ring is too large to be incorporated silently. It cannot be diffuse enough to have escaped detection without being too diffuse to have produced the ring in the first place. Each accommodation of the collision model creates a new constraint that the model then fails to satisfy. Occasionally in science, missing evidence is explained by the limits of available instruments rather than the absence of the thing being looked for. Absence of evidence becomes evidence of absence only when the instruments are sensitive enough that, if the object were there, they would find it. Over 7 decades, the instruments trained on Hoag's object have improved substantially. The field around it has been imaged repeatedly, at increasing depth, in increasing numbers of wavelengths. Each successive generation of data has extended the search without finding what it is looking for. At some point, the continued non-detection shifts from being a limitation of the search to being a result of the search. The impactor's absence might be the most important single measurement in the entire Hoag's object problem. Not because it definitively rules out a collision, but because it eliminates the simplest, cleanest version of the collision hypothesis and forces any surviving version to carry a list of additional assumptions that grow more constraining with each new survey. A hypothesis that requires its primary agent to have disappeared without trace, in a specific way that happens not to leave any of the expected aftereffects, while producing a ring more perfect than the mechanism typically produces, is a hypothesis that is doing a lot of work to remain viable. Somewhere there may be the remnant of a galaxy that shaped everything we have been describing. Or the ring formed without a collision, through a mechanism that does not require an impactor at all, and there is no missing galaxy, because there was never a galaxy to begin with. The field around Hoag's object is quiet. The core is undisturbed. The surrounding surveys have found nothing. The case for the missing impactor remains exactly that, missing, and therefore still a case. Circles are rare in nature, not because they are difficult to draw, but because they require either symmetric initial conditions or ongoing maintenance. A soap bubble is circular because surface tension minimizes area uniformly in all directions simultaneously, and it maintains that shape as long as the pressure differential between its interior and exterior remains balanced. A planetary orbit is approximately circular when initial angular momentum and velocity happen to produce a specific ratio to the central mass, a ratio that, in practice, most orbiting bodies do not achieve, which is why most orbits are ellipses rather than circles. Wherever you encounter a near-perfect circle in a physical system, something imposed that symmetry either at the moment of formation or over time through a process that continuously corrects deviations. Circles do not emerge from chaotic or asymmetric processes. They are signatures of constraint. Hoag's ring is very nearly a perfect circle. That sentence carries more scientific weight than it appears to at first reading, because it is a measurement, not a description. Astronomers quantify the shape of an extended object by measuring its ellipticity, which compares the object's longest dimension to its shortest. For a perfect circle, the longest and shortest dimensions are equal, and the ellipticity equals 0. For an elongated ellipse, the ellipticity is positive and increases toward 1 as the elongation becomes more extreme. Real galaxies, real rings, real galactic structures of any kind tend to have measurable ellipticity because the processes that form them, tidal interactions, angular momentum, asymmetric collapse, do not naturally produce perfect bilateral symmetry. Most ring galaxies observed in large photometric surveys have ellipticities well above zero. Their rings are recognizably elliptical, or partial, or irregular in brightness around their circumference. Hoag's ring has an ellipticity close to zero. Depending on the analysis and the imaging data used, estimates place it among the most circular large-scale structures cataloged in the known galaxy population. The deviation from a perfect circle is present but small, far smaller than what the collision mechanism typically predicts for any but the most constrained initial conditions. Understanding why this creates a problem requires knowing what collision geometry actually produces. When an impacting galaxy falls perpendicular to the disk of the target galaxy and strikes dead center, the resulting density wave propagates outward symmetrically in all directions and produces a ring that is, in principle, close to circular. As the impact geometry deviates from this ideal, the resulting ring deforms. An off-center impact produces a ring that is brighter on the side nearer the impact point, where the density wave was initially stronger. A non-perpendicular approach produces a ring that is elongated along the plane defined by the impactor's trajectory, because the wave propagates faster in one direction than another. Real impactors do not arrive from exactly the right angle at exactly the right point. They arrive from whatever angle and toward whatever point their orbital trajectory happens to describe, which is determined by the encounter history of two galaxies that have no reason to be optimally configured for producing perfect rings. Simulations of ring galaxy formation make this quantitative. Running large numbers of collision scenarios across a wide parameter space of impact velocities, angles, mass ratios, and impact parameters, researchers find that near-circular rings require impact parameters within a narrow tolerance. The impactor must approach within a few degrees of perpendicular and strike within a small angular radius of the center of mass. The fraction of all simulated collisions that naturally fall within this tolerance is small, far less than what you would obtain from a random distribution of encounter geometries. The universe does not arrange galactic encounters to be optimally centered. Encounters that produce near-perfect rings are unusual in the simulated population. Even when simulations are initialized with ideal geometry, the resulting ring is not always as circular as Hoag's. The impacting galaxy is not a point mass. It has a finite size and an internal mass distribution that is not perfectly symmetric. As it passes through the disk, different parts of the impactor interact gravitationally with different parts of the disk at slightly different times. The density wave that propagates outward carries these asymmetries with it, producing azimuthal variations in the ring's brightness. Regions where more gas was compressed and more stars formed, adjacent to regions where the compression was slightly less. Observations of the Cartwheel Galaxy show exactly this. The outer ring is not uniformly bright around its circumference. It has brighter knots and fainter arcs, encoding the specific geometry of the impact that produced it. Hoag's ring is more uniform in brightness than most collision-produced rings in published simulations. The azimuthal variations that the impactor's finite mass should have imprinted are either absent or suppressed below the noise level of current imaging. One proposal for resolving this is post-formation circularization. Stars in the ring do not orbit in perfectly synchronous lockstep. Each star is on its own slightly individual orbit, with a slightly different period depending on its precise distance from the center of the system. Over time, stars at slightly different radii complete their orbits at slightly different rates. This differential rotation means that a ring that was initially asymmetric will gradually become more symmetric as the stars spread around the full circumference and the brighter clumps disperse into a more uniform distribution. Given enough time, this process could, in principle, smooth the azimuthal brightness variations left by an asymmetric collision and produce something that looks more circular than the initial impact geometry would have directly generated. The problem with this rescue is that it conflicts with another observed property of the ring. Differential rotation does not only smooth azimuthal brightness variations, it also broadens the ring radially. Stars drifting along the ring circumference also drift slightly inward or outward over time because their orbital parameters are not identical. The ring width increases. The boundaries between the ring and the gap, and between the ring and the outer intergalactic medium, blur as stars spread beyond the narrow radial zone they initially occupied. The sharp inner and outer edges of Hoag's ring, which persist in deep imaging across multiple observational epochs, should not survive long periods of differential orbital mixing. The process that would circularize the azimuthal distribution is the same process that would destroy the radial sharpness. Hoag's ring is both azimuthally uniform and radially sharp. Differential rotation over the timescale required for circularization would have substantially compromised at least one of those two properties. The ring cannot be simultaneously old enough to have circularized and young enough to still have sharp edges under the dynamics of differential rotation alone. Sitting with that contradiction is not a comfortable place for the collision model. The ring's near-perfect circularity requires either an extraordinarily precise initial impact geometry or a post-formation process that circularized it while leaving the edges sharp. The first option is statistically rare. The second option is mechanically inconsistent with the edge sharpness we observe. The collision model can invoke one of these or the other. It cannot comfortably invoke both simultaneously. Beyond the collision picture, the circularity problem applies to alternative formation mechanisms as well. A dissolved bar instability, in which a galactic bar sheds material from its ends into an outward ring, also does not naturally produce perfect circles. Bars are elongated by definition, and material leaving their tips traces a ring that initially carries the bar's orientation as an imprinted asymmetry. Polar ring capture, in which gas acquired from outside the galaxy settles into a ring orbiting perpendicular to the main galaxy, produces rings that can be close to circular, but depends on the specific dynamics of the captured gas stream, which is rarely perfectly symmetric. Every proposed mechanism faces the same fundamental challenge. The processes that form galactic-scale rings in the real universe are not symmetric enough to naturally produce something this circular, and the processes that could symmetrize a ring after formation have side effects that the ring does not show. Measurements of the ring's ellipticity produce a number. That number is close to zero. What that number means for the physics of ring formation is that the configuration we observe sits in a very narrow region of the space of possible outcomes, a region that every known formation mechanism approaches only under unusual conditions. The number itself is the scientific content here. A different galaxy might have presented an interesting shape to classify and move on from. Hoag's object presents a constraint. Whatever produced this ring was either extraordinarily precisely configured, or it operated through a mechanism that has not yet been adequately described. Perfect circularity is not just an aesthetic feature. It places demands on any explanation that current models struggle to meet while simultaneously satisfying all the other constraints the system imposes. Everything visible in Hoag's object accounts for a minority of the system's total mass. This is not a property specific to Hoag's object. It is a property of galaxies in general, established through decades of observation across hundreds of different galaxy types, sizes, environments, and evolutionary histories. The stars detectable in optical light, the gas measurable in radio, the dust traceable in infrared. All of it together represents roughly 10 to 15% of the matter in a typical large galaxy. The remaining 85 to 90% is dark matter, a component that interacts gravitationally with everything around it and through no other known force, produces no electromagnetic radiation at any wavelength, leaves no chemical signature in any spectrum, and is detectable only through the motions it imposes on the matter we can observe. Knowing it is there without being able to see it requires a specific kind of evidence, and that evidence comes from how things move. When a star orbits the center of a galaxy, its orbital velocity is determined by the total mass enclosed within its orbit. This is a direct consequence of gravity. The more mass inside your orbit, the faster you must move to maintain a stable path rather than falling inward. In the solar system, where nearly all the mass is concentrated in the Sun, objects farther from the center orbit more slowly. Mercury moves faster than Venus, Venus faster than Earth, and so on outward to Neptune. This pattern, called Keplerian fall-off after Johannes Kepler, who described it for planets, is what you expect when mass is concentrated at the center and nothing significant extends beyond the orbits you are measuring. Galaxies do not follow this pattern. When astronomers measure orbital velocities of stars and gas at increasing distances from a galaxy's center, the velocities should fall off at large radii once you are beyond the visible stellar concentration. Instead, in galaxy after galaxy, measured across a wide range of morphologies and environments over more than 4 decades of radio and optical observation, the velocity curve flattens or rises at large radii rather than falling. Stars far from the center orbit as fast as stars much closer in. The only interpretation consistent with gravity as we understand it is that the mass enclosed within an orbit keeps increasing with radius even beyond where any visible matter is detected. Something extends outward past the visible edge, contributing mass without contributing light. This is what rotation curves measure: the gravitational presence of an extended invisible structure that surrounds and outweighs the visible galaxy. Rotation curve data for Hoag's object, obtained through spectroscopic measurements of stellar and gas velocities across the ring, indicates that the ring is orbiting within a substantial dark matter halo. The total mass enclosed within the ring's radius, inferred from orbital velocities, substantially exceeds the mass of the visible stellar populations in both the ring and the core. The dark matter halo extends well beyond the outer ring, as expected for a galaxy of Hoag's total luminosity and scale, providing the gravitational envelope within which the entire visible system sits. This much is consistent with what we would predict for any galaxy of this size. The unusual questions about dark matter in this system are not about whether it is present. They are about its shape, and whether its shape is incidental to or responsible for the structure we observe. In standard cosmological models, dark matter halos form roughly spherical or slightly oblate structures around galaxies. They are not perfectly symmetric. Simulations show they tend to be triaxial, with 3 slightly different principal axes, but they do not naturally develop strong toroidal or ring-like density concentrations under ordinary formation conditions. The visible matter inside the halo organizes itself into whatever configuration its angular momentum, gas dynamics, and star formation history produce, largely independently of the halo's specific shape at the scales of galactic disks. For most galaxies, the halo provides the gravitational well, and the visible matter settles into it without the halo's shape being the primary determinant of the visible galaxy's morphology. For ring galaxies, a small number of researchers have proposed that this independence may break down in an important way. If the dark matter halo of a ring galaxy had a density enhancement at the radius corresponding to the visible ring, a slight concentration of dark matter in a torus-like distribution at that specific orbital radius, rather than a smooth spherical fall-off, this locally enhanced density would provide additional gravitational scaffolding precisely where the ring sits. Stars in the ring would orbit within a region of locally higher gravitational potential, which would help maintain the ring's coherence against differential rotation and resist the radial spreading that should gradually blur its edges. The sharp inner and outer boundaries of Hoag's ring, which have persisted across observational epochs separated by years of imaging, would be more natural if the dark matter at that radius were helping to define and maintain them. The same toroidal density enhancement could play a role not just in maintaining the ring but in explaining where it formed. If a pre-existing dark matter density concentration existed at a specific radius before the ring's star formation was triggered, then any density wave or compression event passing through the disk would preferentially drive gas toward that radius where the combined gravitational potential reaches a local enhancement. Star formation would concentrate at the radius the dark matter preferred, and the ring that resulted would be centered there not purely because of the geometry of the triggering event, but because the underlying mass distribution channeled the response to that event into a preferred configuration. A single dark matter structure would simultaneously explain where the ring formed and why it has remained where it formed. One mechanism, two problems addressed. The difficulty is that this proposal, appealing as it is for the economy of its explanatory reach, is not observationally confirmed for Hoag's object or for ring galaxies as a class. Toroidal dark matter density enhancements are not a predicted output of standard structure formation physics. Current cosmological simulations, which can model dark matter halo formation across a wide range of environments and masses, do not routinely produce toroidal density features at galactic radii under standard initial conditions. Any model invoking a toroidal dark matter architecture for Hoag's object would need to explain how that structure arose in the first place, whether through an unusual collapse history, a specific interaction event, or some other process not yet identified. The proposal moves the question backward one level rather than eliminating it. Dark matter is almost certainly present in the gap as well, and it is worth being precise about what that means. Dark matter does not cluster into stars or gas clouds. It distributes through the gravitational potential of the system according to its own dynamics, which respond to the overall mass distribution rather than to the local density of ordinary matter. If the halo is roughly spherical, dark matter fills the gap continuously, and the gap is a void in ordinary matter only. If the halo has the toroidal density variation some researchers have proposed, the gap could correspond to a region of locally lower dark matter density, sandwiched between the higher density at the core and the ring. Which of these is true has large consequences for interpreting the gap's emptiness. In the first case, the gap is simply a region from which ordinary matter was evacuated while dark matter remained. In the second case, the gap corresponds to a genuine underdensity in total matter, which would impose different constraints on what produced it. The two scenarios have different implications for every formation mechanism discussed so far. Resolving this requires measuring dark matter density at the spatial scale of Hoag's gap, approximately 25,000 light-years, at a distance of 600 million light-years. Gravitational lensing provides the most direct method of mapping dark matter in systems we cannot kinematically resolve in detail. Strong lensing, which produces multiple images or arcs of background sources, requires a mass concentration higher than a gap region in a non-cluster environment provides. Weak lensing, which measures statistical distortions in the shapes of many background galaxies simultaneously, can map dark matter in clusters and large-scale structures, but does not currently achieve the spatial resolution needed to distinguish dark matter density at the scale of Hoag's gap from within the surrounding halo. The kinematic approach, using the motions of tracers within the gap to infer the local gravitational potential, is limited by the very emptiness of the gap itself. There are too few detectable stars within it to provide a statistically useful velocity sample. There is a specific strangeness to building a model of a system around a component you have never directly observed, in a region you cannot resolve, at a distance where the measurements you would need are beyond current reach. Everything we can say about dark matter in Hoag's object is inferred from velocities, from mass budgets, from the gap between what the visible matter weighs and what the dynamics require. The inference is sound. It rests on the same physics that has been confirmed across thousands of other systems, but its specific application to the gap, to the ring, to the question of whether the halo's shape is causal or incidental, requires data that does not yet exist. The invisible architecture of this system may be its organizing principle. Whether it is, remains precisely as open as the question of where the ring formed. The stars in Hoag's ring are moving at velocities that imply a mass far larger than the ring itself contains. Something extends beyond what the image shows, shaping the gravitational environment within which the ring exists. We cannot see it, but its presence is not in doubt. Whether its shape, spherical, oblate, or something more structured, is the reason this ring formed where it did, and has held its shape as long as it has is exactly the kind of question that waits on instruments still being built, pointed at a system that has been quietly resisting explanation for longer than most of those instruments have existed. Somewhere in the dark band of space between Hoag's ring and its core, in the 2001 Hubble Advanced Camera for Survey's image, there is a faint object that rewards close attention. It does not announce itself. In a casual reading of the image, it sits quietly in the gap, easily overlooked against the darkness, roughly centered between the inner edge of the ring and the outer edge of the core. On careful inspection, it resolves into a structure that is not a star and not a smear of noise. It has shape, and the shape it has is a ring. Obtaining a spectrum of this object produces a redshift substantially higher than Hoag's object's value of z equals 0.045. The two objects are not at the same distance. The background ring is far beyond Hoag's object in space, located at a greater distance along the same line of sight, visible through Hoag's gap only because the geometry of the observation placed Hoag's nearly empty interior directly between us and whatever lies behind it. The two objects share no physical connection. They are not interacting. Neither has shaped the other in any way. The alignment is a projection coincidence produced entirely by viewing angle, which in astronomy is common enough in principle, but highly specific in its details here. Calculating the probability of this specific alignment requires knowing two things: the fraction of sky subtended by Hoag's gap, and the number density of ring galaxies per unit area of sky at the redshifts beyond Hoag's object. The first is straightforward. Hoag's gap occupies a definite angular area on the sky, calculable from the ring's angular diameter and the gap width at Hoag's distance. The second is where the calculation becomes genuinely complicated, because the number density of ring galaxies in any direction depends on how many ring galaxies actually exist, which is precisely what we do not know with confidence. Published galaxy morphology catalogs place ring galaxies, broadly defined, at less than 0.1% of all observed galaxies. If that fraction is taken at face value and applied to the sky behind Hoag's gap, the probability of finding any ring galaxy centered within that field is small. The probability of finding one visually aligned with the gap specifically is smaller still. The alignment we observe is not impossible. Any alignment that is observed cannot by definition be impossible. But the probability that random chance placed this particular background object at this particular position, centered within the gap of one of the most unusual ring galaxies in the catalogs, is low enough that it prompted genuine statistical discussion in the literature after the image was published. That discussion led to something more interesting than a probability estimate. It exposed a circularity in how ring galaxy statistics are compiled. To determine whether the Hoag's gap alignment is a rare coincidence or consistent with a higher than expected ring galaxy frequency, you need an accurate count of ring galaxies per unit volume. But the count of ring galaxies per unit volume depends on how confidently we can identify ring galaxies in photometric surveys, which depends on viewing angle, which is a variable the surveys do not fully control. A ring galaxy viewed face-on, so that we are looking through the plane of the ring from above or below, presents its ring structure most clearly and is most likely to be classified correctly. A ring galaxy viewed at a high inclination does not look like a ring. It looks like two roughly parallel lines of stars, or an elongated elliptical smudge, or an irregular structure depending on how much of the ring's thickness is resolved. Most automated classification algorithms applied to large photometric surveys will not identify it as a ring galaxy. It will be counted as something else. A ring galaxy seen at an intermediate inclination is more ambiguous still. Depending on the ring's thickness, the gap's width, and the surface brightness of the core relative to the ring, the system can resemble a lenticular galaxy, a disturbed spiral, or a compact elliptical with a faint outer disk. Human classifiers working through survey data may categorize it correctly or may not, depending on image depth, angular resolution, and the familiarity of the classifier with ring galaxy morphology at that particular quality of data. Machine learning classifiers trained predominantly on spiral and elliptical templates have historically underpredicted morphological rarity classes in survey applications. When astronomers correct for viewing angle by modeling what a population of ring galaxies would look like across all possible orientations, and then asking what fraction of that population would be identified correctly in a given survey, the corrected frequency of ring galaxies rises compared to the uncorrected count. The true space density of ring galaxies is likely higher than the catalog frequency suggests, possibly by a factor of several, though estimates carry real uncertainty because they depend on assumptions about ring geometry and survey completeness that are not fully constrained. If ring galaxies are more common than catalogs reflect, the probability of finding one behind Hoag's gap improves correspondingly, making the coincidence less statistically extreme. The question remains open, but the opening of the question is itself informative. A single image forced a reassessment of whether a category of objects had been systematically undercounted across decades of survey data. Holding these two things together in the same observation is an experience specific to this image. The main subject of the 2001 Hubble image is Hoag's object, with all the unsolved physics that object entails. The secondary object visible through its gap is unrelated to Hoag's object in any causal sense, shares none of its formation history, and contributes nothing to resolving the questions about how Hoag's ring formed or why its gap is empty. And yet, its presence in the image is not scientifically inert. It prompted a legitimate re-examination of ring galaxy statistics. It raised the question of how many such objects exist in a universe that we are observing through a catalog that may systematically miss them when they are tilted away from favorable orientations. Two objects, one image, two entirely independent sets of scientific questions, neither one diminishing the other. The background ring is also a reminder that every dark region in astronomical images is not empty space, it is a window. Every gap in a galaxy, every void between structures, every dark patch between stars in a photographic field contains the light of objects behind it, at distances potentially far greater than whatever is in the foreground. Hoag's gap is an unusually clean window because it is so empty in the foreground. The absence of stars and gas that makes the gap a scientific puzzle also makes it optically transparent in a way that filled galactic interiors are not. Looking through Hoag's gap at the background universe is, in a literal sense, easier than looking through the disk of a normal galaxy, which scatters, absorbs, and reddens background light as it passes through. The same evacuation of ordinary matter that makes the gap scientifically anomalous makes it an unusually unobstructed line of sight into the more distant universe. Observations of the Hoag's gap background with more sensitive instruments. The James Webb Space Telescope's infrared capabilities, for instance, which can detect fainter extended emission than any previous instrument at these wavelengths, could in principle reveal additional background structures not visible in the 2001 Hubble data. A deep infrared image of the gap region might contain multiple faint extended objects at various distances, each one a galaxy in its own right, visible through Hoag's nearly clear interior. What that deeper look would find has not yet been reported in the published literature, and whether the existing Hubble image's background ring is unique within the gap or simply the brightest of several background objects awaits data at sensitivities beyond what the original observation achieved. Two rings in the same image, separated by hundreds of millions of light-years of intervening space, sharing only a line of sight and the shape they happen to have. No causal connection runs between them. The universe did not arrange this for any reason. It arranged it because Hoag's gap is empty enough to be transparent, and because a ring-shaped galaxy happened to sit at the right distance in the right direction, and because we pointed a telescope at Hoag's object during a period of our own history when the instrument existed to resolve what was behind it. The coincidence is real but meaningless as a connection between the two objects. As data about ring galaxy statistics, it is not meaningless at all. And as a demonstration of what a sufficiently dark patch of sky can contain when you look carefully enough, it is its own kind of argument for patience. Everything we have established about Hoag's object has been established from the outside. The redshift, measured at 600 million light-years, the ring's diameter inferred from angular size and distance, the gap's emptiness confirmed across multiple wavelengths, the stellar ages read from spectra, collected by instruments that receive whatever light the system sends in our direction, all of it is external. The physics inside the system is the same physics we have been describing. What changes when you apply it from the inside rather than the outside is not the science. It is what the science means for anything that might exist within the structure we have been measuring. Place a hypothetical observer on a planet orbiting one of Hoag's ring stars. The planet's own star dominates the daytime sky, as any star dominates the sky of its planetary system, irrelevant to the larger structure for most of the day. The night sky is where the ring's geometry becomes the defining feature of existence. Looking along the ring's arc in either direction, the observer sees the combined light of billions of stars concentrated into a narrow band, a sweeping, brilliant arc of blue-white light crossing a significant fraction of the sky. Our own Milky Way band, visible on a dark night from Earth, is the combined light of perhaps 100 to 400 billion stars seen through the plane of the disk, diluted by the enormous range of distances involved, and heavily absorbed by interstellar dust in the spiral arms between the observer and the far side of the galaxy. The ring's stellar population is concentrated into a narrower volume. The dominant stellar types are O-type and B-type stars, each individually more luminous than our Sun by factors of thousands to hundreds of thousands. The band from inside the ring would be intense in a way that the Milky Way band is not, blue-white rather than pale and diffuse, narrow across the sky but bright enough at its peak to cast shadows on a sufficiently dark night. Rotating 90 degrees from the ring arc and looking inward produces an experience that has no analog in any sky we know. In our own galaxy, looking toward the galactic center from our position in the Orion Arm means looking into a progressively denser stellar environment, through the inner disk, through the bulge, toward the concentrated population of stars surrounding Sagittarius A. The sky in the direction of the galactic center from Earth is not dark. It is a brighter region, requiring dark, clear conditions to appreciate, but measurably brighter in star counts than the sky in the direction of the outer disk. From inside Hoag's ring, looking inward produces the opposite. You are looking across the gap, 25,000 light-years of space that our observations have found to contain very few stars, very little gas, and very little dust. The interior of the galaxy in the direction of the center is nearly empty, and it stays nearly empty for the entire distance to the core's outer edge. The core itself, viewed from the ring across that distance, would appear as a diffuse oval of warm yellow-orange light occupying a region of sky roughly several times the angular width of the full moon, as seen from Earth. It would not resolve into individual stars without significant magnification. It would be visible as a concentrated haze, soft at the edges where its stellar population thins, brighter toward the center where the star density is highest, and distinctly warm in color relative to the blue-white arc of the ring on the opposite side of the sky. Between that warm oval and the observer's position, 25,000 light-years of space that our measurements have confirmed is largely devoid of ordinary matter. No intermediate star clusters, no significant interstellar medium to scatter light, the equivalent of the distance from our Sun to the galactic center, but emptier by almost every measure we have applied to it. The radiation environment within the ring is not incidental to these observations. It is physically dominant. O-type and B-type stars produce electromagnetic output weighted heavily toward ultraviolet wavelengths, the spectral range that carries enough energy per photon to break chemical bonds and disrupt the molecular structures that biology depends on. Our Sun is a G-type star whose spectrum peaks in visible light, with its ultraviolet output substantially lower than that of the massive stars in Hoag's ring. At any given orbital distance from a massive ring star that would place a planet in the equivalent of the habitable zone, the ultraviolet flux arriving at the planet's surface would be orders of magnitude higher than what Earth receives from the Sun. Planets around O-type and B-type stars can retain atmospheres capable of shielding surfaces from the worst of this radiation. But the margin between shielded and unshielded is narrower, and the fraction of the spectrum that penetrates regardless of atmospheric composition is larger. The deeper problem for the ring's environment as a setting for biology is not the radiation level at any given moment, but the timescale over which the stellar neighborhood changes. An O-type star lives for a few million years. A B-type star lives for tens of millions at most. Our Sun, by comparison, has been burning stably for approximately 4.6 billion years and has roughly another 5 billion years before exhausting its core hydrogen. Complex multicellular life on Earth required hundreds of millions of years to establish the body plans, ecological relationships, and environmental stability that eventually allowed intelligence to arise. The ring's most massive stars complete their entire lives in a fraction of the time Earth's first multicellular organisms needed to establish themselves. A supernova within a few light-years deposits enough energy and ionizing radiation and blast material to strip planetary atmospheres and sterilize surfaces. In a stellar environment where supernovae occur across the ring's population every few million years, any planetary system in the ring is repeatedly exposed to the aftermath of nearby stellar deaths on timescales too short for complex life to have had time to establish a meaningful foothold before the next disruption arrives. Planetary formation around massive stars is not impossible. Protoplanetary disks have been observed around B-type stars, and rocky planets can accumulate from disk material even in high radiation environments, though the gas that would produce giant planets tends to be photoevaporated before it can efficiently accrete onto planetary cores. The planets that form in these environments may be predominantly rocky and compact, rather than the gas giant-dominated architectures common around solar-type stars. Whether they retain significant atmospheres, develop hydrological cycles, or maintain the chemical conditions that allow self-replicating chemistry to begin is genuinely unknown and depends on factors that current theory cannot fully constrain for high-mass stellar environments at Hoag's distance from us. From a gravitational standpoint, a star in Hoag's ring occupies a simpler dynamical environment than our Sun does within the Milky Way. The Sun's orbit through the Milky Way is perturbed by the bar, by the spiral arms, by the concentrated mass of the inner bulge, and by encounters with molecular clouds, a complex, time-varying gravitational landscape that causes the Sun to bob above and below the galactic plane and drift radially inward and outward over galactic timescales. A star in Hoag's ring orbits primarily under the combined influence of the ring's self-gravity and the gravitational field of the distant core, without the perturbative influence of a bar or multiple spiral arms. Its orbit is closer to a stable circle than most galactic orbits. The gravitational environment is cleaner at the cost of the ring being the entire galaxy available. There are no spiral arms to migrate through, no inner disk to drift toward, no bar resonances to drive long-term orbital evolution. The ring is both the star's neighborhood and the boundary of the galaxy it can call home. From any position within the ring, looking inward exposes a specific and unusual topology. There is a direction in the sky that points across 25,000 light-years of near-empty space toward a warm concentration of old stars at the far side. There is a diametrically opposite direction that opens directly into the intergalactic void, toward the nearest neighboring galaxies hundreds of thousands of light-years away. These two directions, inward toward the core, outward toward nothing, would be the most immediately legible features of the sky. In our own position within the Milky Way, no such clear topology exists at galactic scales. The disk fills our equatorial sky in all horizontal directions with roughly comparable star densities, and the galactic center is a brighter region in one specific direction, rather than the only visible concentration of stars across a hemisphere of empty sky. The gap that makes Hoag's object scientifically anomalous from our vantage point would be, from inside the ring, simply the sky. Half of it would always be empty. Half of it would always blaze with light. The properties of Hoag's ring, The stellar types, the radiation levels, the supernova frequency, the gap's width, the core's distance, become physical constraints on everything within the system when read from the inside. The gap is not just empty in our observations, it is empty in every direction that an interior observer would look inward across. The ring is not just geometrically striking from 600 million light-years away. From inside it, it is a band of blue-white fire occupying one half of the sky, and the other half is a dark gulf with a warm, distant haze at its far end and nothing in between. The physics is the same in either perspective. What changes is which part of it presses most directly on whatever is there. Stars do not orbit at the same speed regardless of where they sit in a galaxy. This is not a property specific to ring galaxies or to unusual systems. It is a universal feature of gravitational dynamics in extended mass distributions. The orbital velocity of any object depends on the total mass enclosed within its orbit, and because mass in galaxies is distributed rather than concentrated at a central point, stars at different radii experience different enclosed masses and orbit at different speeds. In the outer regions of most galaxies, where the rotation curve has flattened a star slightly farther from the center, takes somewhat longer to complete one full orbit than a star slightly closer in. Over one orbit, the difference is small. Over hundreds of millions of orbits, the cumulative displacement is not. Differential rotation does not stay abstract for long when you apply it to a ring structure. Imagine the ring at the moment its stars finish forming, a coherent narrow band of new stars at a specific range of radii from the center, arranged in the near-perfect circle we observe. Each of those stars immediately begins drifting on its own individual orbit, slightly different from its neighbors. A star 100 light-years farther from the center than another will take slightly longer to complete its circuit. Over 10 million years, the displacement is small but non-zero. Over 100 million years, stars that were initially adjacent around the ring's circumference have developed measurable phase differences. Over 500 million years, the phase differences have accumulated enough that the ring has spread. Azimuthal gaps have appeared where the slower stars have fallen behind, and the ring's edges have blurred as stars drift inward and outward from the narrow radial band they initially occupied. The ring does not shatter, it thickens. It develops azimuthal asymmetries. The sharp structure we currently observe evolves into something broader, more diffuse, and less ring-like with time. Making this quantitative requires knowing how fast the ring stars are orbiting and at what radius. Hoag's ring sits at an outer diameter of approximately 120,000 light-years, placing the ring stars at roughly 60,000 light-years from the center. At an orbital velocity inferred from rotation curve data of approximately 200 to 250 kilometers per second, the orbital period for a star at that radius is approximately 400 to 500 million years. One full circuit of the galaxy in roughly 500 million years. The differential rotation rate across the ring's radial width, which spans several thousand light-years from inner to outer edge, would produce measurable phase spreading on a timescale of 1 to a few orbital periods between several hundred million years and approximately 1 to 2 billion years, depending on the ring's initial width and the steepness of the rotation curve at that radius. Hoag's ring remains sharp at both boundaries. The inner edge, where the ring meets the gap, and the outer edge, where the ring meets the intergalactic medium, are both well defined in the 2001 Hubble imaging and in follow-up observations. These edges are not smeared into gradients. They are not developing the broad annular profile that differential rotation eventually produces. They are edges. Older ring systems observed in surveys show us what the dispersal process looks like at more advanced stages. Several galaxies in wide-field photometric catalogs present as broad, diffuse annular structures rather than sharp rings. A wide band of relatively uniform low-surface brightness encircling a galactic center, with no sharp inner or outer boundary, exhibiting the smooth brightness profile that differential rotation produces when operating for timescales of billions of years on what was once a compact ring. These systems are not classified in most catalogs as ring galaxies in the same category as Hoag's object or the cartwheel. They appear as peculiar lenticulars, or as galaxies with unusual outer disks. But their structure is consistent with the late evolutionary state of a ring system that formed through a triggering event and then evolved under differential rotation without any mechanism to maintain the ring's coherence. What we are looking at in those systems is Hoag's object's probable future, at a distance of hundreds of millions to a billion years. Two mechanisms have been proposed for maintaining ring coherence against differential rotation long enough to explain what we observe in Hoag's object. The first is the ring's own self-gravity. If the ring contains enough mass, the mutual gravitational attraction between stars within the ring creates a potential well that resists the radial spreading differential rotation would otherwise produce. Stars drifting outward from the ring's center of mass are pulled back by the combined gravity of the stars behind them. Stars drifting inward are similarly retarded. The ring acts as its own gravitational cage, keeping its width narrow and its edges sharp by attracting straying members back into the main concentration. Self-gravity in galactic rings is a real effect, but its magnitude depends on the ring's mass density per unit length around the circumference. For Hoag's ring, with a total stellar mass of billions of solar masses distributed across a circumference of hundreds of thousands of light-years, estimates of the self-gravity suggest it can slow the dispersal but not halt it indefinitely. It extends the ring's lifetime without solving the fundamental problem that differential rotation poses over timescales of a billion years or more. The second proposal invokes the dark matter halo's structure, as discussed in the context of the ring's formation. If the dark matter density has a local enhancement at the ring's radius, then stars in the ring would orbit in a minimum of the local potential rather than in a featureless gradient. Stars, displaced inward or outward, would roll back toward the potential minimum the way a marble rolls back to the bottom of a bowl. This would maintain the ring's radial sharpness against differential spreading on timescales much longer than the ring's current age, potentially indefinitely as long as the dark matter structure itself persists. The same toroidal structure that would have guided where the ring formed in the first place would become the maintenance mechanism that keeps it sharp once formed. The dark matter architecture would solve both the formation question and the longevity question in a single structure. Neither proposal has been confirmed observationally for Hoag's object. Self-gravity is plausible, but insufficient alone at long timescales. The toroidal dark matter enhancement is appealing, but not predicted by standard structure formation theory, and not measurable at the spatial resolution current instruments can achieve at Hoag's distance. The ring is sharp. The explanations for why it remains sharp are incomplete. Sitting at the center of this is a timing problem that has a specific statistical texture. If the ring is genuinely young, then we are observing it in the early phase of its existence, before differential rotation has had time to substantially blur its structure. The ring is sharp because it has not had time to become anything else. This explanation requires no exotic maintenance mechanism. It requires only that the ring's formation was recent. But it requires something else that is less comfortable. It requires us to be observing this specific galaxy during a brief window of its total lifespan. The universe is approximately 13.8 billion years old. Hoag's object formed its ring within the last few 100 million years. It will have dispersed that ring into a broad annular structure within the next billion years or so. The window during which the ring presents as a sharp, near-perfect circle is perhaps 1 to 2 billion years wide within a cosmic history 14 billion years long, roughly 10 to 15% of the universe's current age. The probability that an observer in the present era happens to be looking at this particular galaxy within that window, rather than before the ring formed or after it dispersed, is not negligible, but it is a consideration. If ring galaxies spend most of their existence either in the pre-ring phase or in the post-dispersal phase, then sharp ring systems like Hoag's object represent a snapshot of a brief middle period, and observing one requires a certain alignment of timing across observer and observed. The alternative removes the timing problem, but introduces a different one. A mechanism capable of maintaining galactic-scale ring coherence for billions of years is not something our current models predict or describe. Identifying such a mechanism would require explaining not just Hoag's object, but why other ring galaxies do not appear to share this longevity, why most observed ring systems show the dispersal signatures consistent with ordinary differential rotation, while Hoag's does not. The mechanism would have to be specific to the conditions of this system in a way that is not yet understood and that has not yet produced testable predictions distinguishable from the youth hypothesis. A transient structure observed at peak clarity, or a persistent structure maintained by something outside our current models. Both options change the interpretation of everything else we have established about this system. A young ring means the formation event was recent, which constrains the timeline in ways that interact with the impactor problem and the age of the core. A maintained ring means the dark matter architecture or some other factor is playing an active role in the galaxy's current structure, which changes the questions we need to ask about how this system has evolved. The ring is sharp. The reason it is sharp is one of the questions this galaxy has not yet answered. Every explanation discussed so far carries an assumption so fundamental that it rarely gets named explicitly. The assumption is that Hoag's ring and Hoag's core belong to the same formation event, that they are products of a single history, however unusual, rather than two separate systems that assembled through entirely different processes and ended up sharing the same gravitational address. Drop that assumption, and the problem changes shape. The ring's youth and the core's age are no longer paradoxical features of a single object. They become the natural signatures of two objects with separate biographies that came to share an orbit. Whether that reframing helps depends on whether independent assembly is physically plausible. A ring of stars orbiting an existing galactic core without having formed from the same event requires a mechanism for acquisition. The ring material, or the gas from which it formed, must have been captured from an external source, must have retained or developed enough angular momentum to settle into a roughly circular orbit around the existing core, and must have done so without significantly disturbing the core's existing stellar population or its dynamical structure. Each of those requirements carries observational consequences, and the consequences either appear in the data or they do not. Polar ring galaxies provide the best documented case of genuine two-component galactic systems assembled from separate sources. In a polar ring galaxy, a ring of stars and gas orbits perpendicular or nearly perpendicular to the equatorial plane of a central galaxy, the two components sharing a common center of mass but carrying different angular momenta from different accretion events. The ring material is typically acquired from an external source, that donated material with an angular momentum vector approximately perpendicular to the host galaxy's spin axis. The resulting system genuinely contains two components with different formation histories occupying the same gravitational potential. Applying the polar ring framework to Hoag's object requires the ring to orbit at a large inclination relative to the core. If Hoag's ring were inclined at something close to 90 degrees to the core's rotation axis, then viewed from a specific direction in space, it could appear as a roughly centered ring surrounding the core rather than as an obviously perpendicular structure. The viewing angle would be doing substantial work in making the system look like a coplanar ring. For this to be the case, the kinematic data should show the two components rotating with angular momentum vectors pointing in dramatically different directions. Spectroscopic observations of the ring's rotation have not shown this. The ring appears to rotate in a plane roughly consistent with the core's orientation, without the large inclination difference that would characterize a polar ring system. The polar ring hypothesis requires a kinematic signature that the data, at available precision, does not provide. A coplanar captured ring, external material accreted with angular momentum aligned with the core's rotation, settling into the equatorial plane rather than into a polar orbit, is harder to rule out purely on geometric grounds. Material accreted from a coplanar source, such as gas stripped from a companion galaxy during a tidal encounter that did not involve a direct impact, could in principle settle into a roughly circular orbit at a large radius around the existing core. If the accreted gas was dense enough, it would eventually reach the Jeans threshold and form stars, producing a ring of young stars around an old core without requiring a head-on collision. The gap between the ring and core could represent the region interior to the accreted gas, which settled preferentially at larger radii where the specific angular momentum of the captured material placed it. The coplanar capture scenario has traction precisely where the collision model has its most serious difficulties. It does not require a missing impactor, because the tidal interaction responsible for stripping the gas could have occurred long enough ago that the donor galaxy has since receded to a distance currently below survey sensitivity, or has itself evolved into a low surface brightness system. It does not require the core to have been disturbed, because a tidal gas accretion event at large radius need not significantly perturb the inner regions of the host system. It allows the ring's young age to be entirely decoupled from the core's old age, since the ring material would have arrived recently regardless of when the core formed. What the coplanar capture scenario struggles to explain is the ring's near-perfect circularity. Tidally stripped gas streams are not circular. They arrive as elongated arcs, as clumpy asymmetric debris, or as sheets of material that then must circularize under the host system's gravitational field over time. The circularization process faces exactly the same edge-blurring problem discussed in the context of post-formation dynamics. The process that rounds the ring also thickens it. A third mechanism requires no external material at all. In many spiral and barred spiral galaxies, a rotating elongated structure called a bar forms spontaneously from disk instabilities. The bar extends from the core outward along a specific axis, channeling gas inward toward the center, while also funneling material outward along its tips. As the bar evolves, it can dissolve, the elongated structure breaking up as its constituent stars shift from ordered bar orbits to rounder orbital families, and the material that was at the bar's tip spreads outward and can settle into a ring-like structure outside the core. The resulting system has a ring, a gap between the ring and the core where the bar was, and a central concentration of older stars. It requires no external collision, no missing impactor, and no captured ring material. Everything comes from within. Dissolved bar formation succeeds in reproducing several of Hoag's structural features better than any collision-based scenario. The gap emerges naturally as the region depleted when the bar material was redistributed. The core remains undisturbed, because the bar formation and dissolution operate through internal dynamics that do not shock the central stellar population the way a collision would. The geometry produces a ring around a pre-existing core without requiring any external agent, which eliminates the impactor problem entirely. At the level of large-scale morphology, the dissolved bar hypothesis accounts for the gap, the core, and the ring's approximate location more cleanly than any scenario requiring a missing interacting galaxy. The failure arrives at the ring's stellar population. Bar dissolution does not trigger a burst of star formation. The material that spreads from the bar's tips as the bar dissolves consists primarily of stars that were already old when they were in the bar, redistributed into new orbits, but not newly born. If Hoag's ring formed through bar dissolution, the ring should contain predominantly old stars, similar in age to the core population, perhaps somewhat younger if the bar itself was younger than the oldest core stars, but not the young blue-white O-type and B-type stars that dominate the ring's observed spectral signature. The ring's stellar population is not old stars redistributed. It is young stars freshly formed from recently triggered star formation. Bar dissolution moves existing stars. It does not produce the conditions for compressing gas into a burst of new stellar birth across the full circumference of the ring. Explaining the ring's age requires a trigger that bar dissolution does not provide. The kinematic data cuts across all of these alternative scenarios in a way that constrains them without decisively resolving the question. Spectroscopic observations of the ring's rotation direction and the core's rotation direction show that both components rotate in the same sense. The angular momentum vectors of the ring and core are roughly aligned. This is more consistent with a single origin scenario, both components inheriting their rotation from the same initial mass distribution, than with a capture or accretion scenario, where external material arrives with an independently determined angular momentum direction. If the ring were externally acquired, you might expect its rotation to be tilted relative to the core's rotation by some amount reflecting the angular momentum of the incoming material. The co-rotation observed is not a guarantee of single origin. External material accreting from a co-rotating source would also produce aligned rotation, but it reduces the independent assembly scenario's most natural prediction. What accumulates across these alternatives is not a landscape of competing hypotheses with roughly equal evidential standing. It is a map of specific failures. The polar ring hypothesis fails on kinematics. The coplanar capture scenario fails on circularity. The dissolved bar hypothesis fails on stellar age. Each mechanism captures something real: the two-component instinct behind polar rings, the external acquisition instinct behind coplanar capture, the internal redistribution elegance of the bar hypothesis, and each one loses purchase precisely at the feature it cannot account for. The failures are not random. They are each located at the same class of problem. The ring is young, circular, and sharp simultaneously, and no single proposed mechanism produces all three of those properties in a system that also has an undisturbed old core and an empty gap with sharp boundaries. Recognizing that pattern is not a defeat, it is information. A problem that resists every available mechanism in a specific, non-overlapping way is not a problem waiting for the right hypothesis to be applied to it. It is a problem telling you that the hypothesis space itself may be incomplete, that the mechanism that actually produced Hoag's object does not yet appear in the list of mechanisms astronomers have tried. Each failed explanation narrows the territory the correct explanation must navigate. The correct explanation, when it comes, will have to produce a young ring and an undisturbed core, and a sharp empty gap and a near-perfect circle through a single coherent process. The alternatives show us, in precise detail, how difficult that is to achieve. Each alternative explains part of what we see and fails at another part. That pattern is not coincidence. It is the shape of a problem that is not yet solved. Galaxy formation simulations have become one of the most powerful tools in modern astrophysics, not because they simplify the problem of galaxy evolution, but because they do not. The most capable simulation frameworks currently running model gravity, gas hydrodynamics, star formation, stellar feedback from supernovae and stellar winds, black hole growth and feedback, and the large-scale distribution of dark matter simultaneously across volumes of space containing billions of particles. The physics that governs each of these processes is implemented from first principles where possible, and from calibrated subgrid prescriptions where direct modeling is computationally prohibitive. The result is not a cartoon of galaxy evolution. It is a reproduction of the universe complex enough that the simulated galaxy populations it produces have been compared directly to observed galaxy distributions, size-mass relations, color distributions, and morphological frequencies, and they match at a level of fidelity that has validated these frameworks as genuine tools for understanding how galaxies form and evolve across cosmic time. Running these simulations does not require pointing them specifically at Hoag's object. They model large cosmological volumes, tens to hundreds of millions of light-years on a side, and the galaxies that form within those volumes emerge from the initial conditions and the physical laws built into the code rather than from any specified target morphology. Ring galaxies appear spontaneously within these volumes, produced when two galaxies happen to interact in a near head-on collision. Their frequency in simulation outputs is low, consistent with the rarity of ring galaxies in observational surveys. The rings that form are transient, lasting a few 100 million years before differential rotation disperses them. They are, in the broad sense, ring galaxies. Circular structures of elevated stellar density surrounding a central concentration produced by the density wave mechanism that the collision model predicts. At this level of description, the simulations confirm that the mechanism works and produces the right general category of object. Comparing the specific properties of simulated ring galaxies to Hoag's object is where the confirmation ends. Simulated rings are typically not as circular as Hoag's ring. They show azimuthal brightness variations reflecting the finite mass and imperfect geometry of the impacting system. Their inner edges, where the ring meets the lower density interior region, are less sharply defined than what high-resolution imaging of Hoag's object reveals. The gap-equivalent region in simulated ring systems, where present, tends to contain more residual gas and more scattered stars than Hoag's gap shows across its multi-wavelength observations. The age contrast between the ring stellar population and the central stellar population exists in simulated systems but is often less extreme than Hoag's bimodal distribution, and intermediate age populations occasionally appear in the gap region where Hoag's gap shows very little. These are not catastrophic failures. They are systematic discrepancies, present at the level of detail that distinguishes Hoag's object from a generic ring galaxy, which is precisely the level that matters. Attempting to close these discrepancies by adjusting the initial conditions of the simulation reveals the core of the problem. Making the ring more circular requires a more precisely centered impact geometry. Moving toward a more precisely centered impact tends to inject more energy into the inner regions of the system, disturbing the central stellar population and producing elevated velocity dispersion in the core stars. Cleaning up the gap by requiring more efficient outward transport of material tends to require higher energy impacts or stronger feedback from the central black hole, both of which produce rings that are less sharply bounded and more disturbed in azimuthal structure. Sharpening the ring edges requires either very young ring ages or an additional maintenance mechanism that standard simulations do not contain by default. Maximizing the age contrast between ring and core while keeping the core undisturbed requires impact geometries in which the impactor passes through the disk without significantly affecting the central mass concentration, which constrains the impactor's mass and trajectory in ways that interact with the circularity requirement in opposing directions. What emerges from this optimization landscape is a specific structure of trade-offs. Circularity and core disturbance pull in opposite directions. Gap emptiness and ring sharpness pull in opposite directions. Core undisturbed and age contrast both require impact geometries that are increasingly constrained and increasingly inconsistent with the conditions that produce good circularity. Published simulation studies that have specifically targeted Hoag-like initial conditions have not produced a single run where all four properties converge simultaneously at the observed levels. Individual properties can be reproduced. 2 or 3 can sometimes be achieved in combination. The fourth property then deviates from observation in a specific way that reflects which trade-off was compromised to achieve the others. The problem is not that no simulation can produce a ring. It is that no simulation has yet produced this ring. Resolution is a genuine variable in this assessment. Cosmological simulations must balance the size of the simulated volume against the spatial resolution achievable within that volume, and achieving the spatial resolution needed to model the detailed structure of a single galaxy's ring, gap, and core simultaneously, while embedding that galaxy within a realistic cosmological environment is computationally expensive. Some of the discrepancies between simulated ring galaxies and Hoag's object may be resolution artifacts. Processes operating at scales below the simulation's resolution limit may be affecting edge sharpness, gap emptiness, and azimuthal uniformity in ways that higher resolution targeted simulations could capture more faithfully. Researchers have pointed to this limitation as a reason to interpret the discrepancies with some caution rather than treating them as definitive evidence of missing physics. Targeted zoom-in simulations, which sacrifice cosmological volume in exchange for dramatically higher spatial resolution within a small target region, provide a test of this possibility. Several groups have run idealized collision simulations specifically designed to reproduce Hoag's object's structural properties at resolutions not achievable in cosmological volumes. The results improve on some properties. The ring's radial sharpness is better captured at higher resolution, and the gas dynamics within the gap region are modeled with greater fidelity. The simultaneous convergence problem does not disappear. Higher resolution brings individual properties into closer agreement with observation while revealing additional structure in the discrepancies. The gap's sharpness improves, but the circularity becomes harder to maintain, or the age contrast sharpens but the core shows disturbances that Hoag's core does not exhibit. The trade-off structure persists at higher resolution. It does not appear to be a resolution artifact. Each time a simulation improves one property and loses ground on another, the failure is telling us something specific about the physics. The fact that the trade-off structure persists across different simulation frameworks, different resolution levels, and different initial condition specifications means the problem is not a parameter search that will eventually converge. It is a structural tension in the available mechanisms. The combinations of physical processes currently built into these simulations are not, in any configuration so far explored, able to produce Hoag's object. The gap between what the simulations can produce and what the observations require is not a gap in computing power or in the size of the parameter space explored. It is a gap between the physics that current models include and the physics that apparently operated in the formation of this system. This is the specific meaning of a simulation failure that is worth holding precisely. When a simulation fails to reproduce an observed property because the parameter space has not been explored thoroughly enough, more computation solves the problem. When a simulation fails to reproduce an observed property because the resolution is insufficient, finer resolution solves the problem. When a simulation fails to reproduce an observed property because the physics built into the model is genuinely incomplete, more computation and finer resolution are not the solution. They make the failure more precise, which is itself informative, but they do not eliminate it. The failure of Hoag's object to emerge from any combination of currently explored initial conditions and currently implemented physics across multiple independent simulation frameworks is consistent with the third category. Something in the physical picture is missing, not merely under-resolved or undersampled. What would need to be true for a simulation to succeed? It would need to produce, in a single coherent run, a ring with near-zero ellipticity, sharp inner and outer boundaries, a gap emptied of ordinary matter to the levels we observe, a ring's stellar population dramatically younger than the core, and a core that registers none of the dynamical disturbance that producing the ring should have imposed on it. If such a simulation result appeared in the literature, the initial conditions and physical assumptions required to produce it would themselves be the scientific content, not proof that the collision mechanism works at last, but a precise specification of the conditions under which it works, which would then become the next set of questions to answer about why those conditions arose in this particular galaxy. The simulations have not found that set of conditions yet. After decades of improving computational capability, expanding parameter exploration, and increasing physical fidelity in the models, Hoag's object remains outside the range of outputs that the best available frameworks reliably produce. That is not a failure of the simulations. The simulations are working as intended. They are accurately reproducing the predictions of the physics they encode. The problem is that those predictions do not converge on what we observe. A problem that survives the best available simulation is not a gap in computing power. It is a signal that the physics as currently understood is missing something that this galaxy contains. Standard cosmological theory rests on a framework called lambda CDM, where lambda refers to the cosmological constant that drives the accelerating expansion of the universe, and CDM stands for cold dark matter. Within this framework, the large-scale structure of the universe emerges from small quantum fluctuations in the early universe that gravity amplified over 13 billion years. Dark matter halos form first, then baryonic matter falls into them, cools, and collapses into stars. Galaxies form and evolve through a combination of smooth gas accretion from the cosmic web, mergers with other galaxies, and feedback from star formation and black holes that regulates how efficiently gas is converted into stars across cosmic time. The framework has produced a predictive account of galaxy populations that matches observations across an enormous range of scales and epochs, from the cosmic microwave background at the edge of the observable universe to the statistical properties of galaxies in local surveys. Its successes are not minor or marginal. They represent one of the most precisely tested theoretical frameworks in the history of science. Understanding where Hoag's object sits relative to this framework requires being careful about what kind of tension it creates. Hoag's object does not refute lambda CDM. It does not break the equations of gravity, or the physics of stellar evolution, or the thermodynamics of gas cooling. Every physical process that has been invoked to explain it, collision-induced density waves, bar dissolution, gas capture, dark matter halo structure, AGN feedback, operates within the lambda CDM framework and is consistent with its fundamental physics. The tension is more specific and more subtle. The framework, implemented in its current form with its current prescriptions for how physical processes are modeled, does not produce an object with Hoag's simultaneous set of properties in any simulation that has been run. That is a tension with the current implementation of the framework rather than with the framework's foundations. Whether that implementation gap reflects missing detail that better modeling will eventually supply, or missing physics that the framework does not currently contain at all, is a question the data does not yet answer decisively. Hoag's object is not alone in creating this kind of tension. Over the past 2 decades, several categories of observed galaxies have accumulated in the literature as objects that standard galaxy formation models struggle to account for naturally. Ultra-diffuse galaxies, discovered in significant numbers beginning in the mid-2010s, are systems with stellar masses comparable to moderate-sized dwarf galaxies but extended across areas comparable to the Milky Way. They are extraordinarily low in surface brightness, which is why they escape detection in earlier surveys, and their internal dynamics suggest dark matter halos far more massive relative to their stellar content than standard abundance matching would predict. Some ultra-diffuse galaxies appear to contain far less dark matter than expected, which is a different kind of tension with models that predict dark matter halos should always accompany galaxy-scale stellar systems. Compact elliptical galaxies at high redshift present a related problem from the other direction. They are as massive as modern giant ellipticals, but occupy a fraction of the physical volume, denser than any comparably massive system in the local universe, and the evolutionary path from high redshift compact elliptical to local massive elliptical is not fully traced in simulation outputs. The James Webb Space Telescope has extended this catalog of anomalies into the early universe. Since beginning science operations, it has detected galaxy candidates at redshifts corresponding to the first few 100 million years of cosmic history that appear more massive, more structured, and more evolved than standard models predicted for that epoch. The most massive of these candidates, if their photometric redshifts and stellar mass estimates are confirmed spectroscopically, would challenge the timeline within which galaxy formation is expected to proceed. The universe would have needed to convert gas into stars at a rate that strains the efficiency limits built into current models. The debate over these objects is active and unresolved. Some researchers argue the most extreme cases will be revised downward in mass when better data is obtained, while others argue they represent genuine evidence that star formation in the early universe was more efficient than models predict. The debate is not settled, but its existence is itself informative. Each generation of more powerful instruments has revealed galaxy populations at the edges of what current models comfortably explain. Placing Hoag's object within this broader landscape does not require claiming it is more important than these other anomalies. or that it points unambiguously toward the same kind of theoretical revision they may require. What it does is establish that Hoag's object is not an isolated curiosity sitting alone outside an otherwise fully adequate theoretical framework. It is one of several categories of galaxy that, taken individually, could be attributed to unlikely but not impossible initial conditions, but that, taken together, describe a pattern of model edges that keeps appearing when observations are pushed into new regimes. The distinction between rare case within existing theory and requires physics outside existing theory is genuinely difficult to draw from the evidence currently available, and the history of astronomy contains cautionary examples in both directions. Pulsars, discovered in 1967, initially appeared to require exotic physics before neutron star theory provided the framework. Quasars, identified in the early 1960s, seemed to violate energy budget constraints until active galactic nucleus theory established the mechanism of accretion onto supermassive black holes. In both cases, the anomaly was real, and the resolution required extending the theoretical framework rather than abandoning it. But the history also contains cases where anomalous objects turned out to be ordinary objects in unusual configurations, requiring no new physics but only a fuller exploration of what existing physics already permitted. The challenge is that at the moment of encounter with an anomaly, it is rarely clear which category it belongs to. Current consensus among researchers who have studied Hoag's object is weighted, if unevenly, toward the former of these positions. The object likely formed through a combination of processes that are individually understood, but that came together in a configuration of unusual specificity. The collision mechanism is not abandoned. The circularity problem, the missing impactor, the undisturbed core, and the age contrast are acknowledged as real constraints that the standard collision picture has not satisfactorily resolved, but they are attributed to a parameter space that has not been fully explored rather than to a missing physical process. This is a reasonable position given the evidence. It is also a position that has been held, with incremental modification, for most of the 7 decades since the object was discovered, during which the parameter space has been explored substantially without producing convergence. The reasonableness of the position does not guarantee that it is correct. What a resolution would actually look like matters for assessing how far away it might be. If Hoag's object formed through a collision under unusually constrained initial conditions, resolution requires finding a set of initial conditions that, when run in a simulation at sufficient resolution, produces all 4 of the system's key properties simultaneously. The conditions would then need to be evaluated for plausibility. Were they unlikely enough to make Hoag's object a genuinely rare outcome of ordinary physics? Or so unlikely that invoking them constitutes a different kind of theoretical failure? If Hoag's object required a formation mechanism not currently included in models, resolution requires identifying that mechanism, implementing it in the theoretical framework, and showing that it produces Hoag's object while remaining consistent with the broad range of observations that lambda CDM already explains. The second path is more difficult and carries higher stakes. Neither path has reached its destination. Sitting at the edge of a theoretical framework, looking at an object that the framework cannot yet account for, is not a comfortable scientific position, nor is it unusual. Most of the major advances in astrophysics over the past century were preceded by a period of accumulated anomalies that did not fit the existing framework, followed by a theoretical extension that accommodated them. The anomalies did not announce their significance. They simply resisted explanation, consistently and specifically, until the explanation that eventually accommodated them turned out to require something the framework had not previously contained. Hoag's object has been resisting explanation consistently and specifically for 75 years. Whether it belongs to the category of anomaly that requires theoretical extension or to the category that requires better parameter exploration is a question that active research is currently pursuing and has not yet closed. Galaxy formation theory is not a finished product. It is a living framework that has been extended repeatedly as observations pushed it into new territory. and that extension has consistently improved its account of how the universe builds the structures we observe. The accumulation of exceptions does not break a theory, but it tells us that the territory the theory covers is smaller than we thought, and that at the edges of that territory, where Hoag's object and a growing catalog of anomalous systems reside, the framework still has work to do. The work is ongoing. The object is still there, circling, waiting. Counting rare things in the universe requires a method that is reliable not only for common things, but for objects whose defining properties make them easy to misidentify or miss entirely. The history of observational astronomy contains repeated instances of object classes that turned out to be far more numerous than initial surveys suggested, not because earlier astronomers were careless, but because the classification algorithms applied to large datasets were trained predominantly on the common morphological types, and rare morphologies were underrepresented in the training data, underpopulated in the classified output, and systematically absorbed into adjacent categories that their unusual appearances superficially resembled. Galaxy morphology classification is particularly susceptible to this problem because galaxy shapes span a continuous space of appearances, and because the same object can look dramatically different depending on how it is oriented relative to the observer. Ring galaxies of all types, including messy collision-produced systems with obvious impactors and asymmetric rings, represent fewer than 0.1% of galaxies in large photometric surveys. That fraction is small, but not surprising given that the collision geometry required to produce a ring, while not vanishingly rare, represents only a fraction of all possible galactic encounter configurations. Most galactic interactions are not head-on. Most encounters that are approximately head-on are not precisely centered. Most encounters that are precisely centered involve mass ratios or velocity dispersions that produce tidal distortions rather than clean ring structures. The fraction of all galactic encounters that proceed through a geometry favorable to ring production is constrained by the geometry of the problem, and the resulting frequency of ring galaxies in the observable universe is consistent with this geometric constraint applied to the observed rate of galaxy interactions. Within the category of ring galaxies broadly defined, Hoag-like objects occupy a much smaller subset. A ring galaxy formed by a clearly documented collision with a visible impactor, tidal features, asymmetric ring brightness, and a gap that contains residual material is a different kind of object from Hoag's object in several properties that are directly observable, isolating only those ring systems that show near-perfect circularity. A clean gap emptied to the levels Hoag's gap shows across multiple wavelengths. A bimodal stellar population with the dramatic age contrast between ring and core that Hoag's spectrum reveals, and no obvious nearby impactor reduces the candidate count substantially. Dedicated searches through published galaxy catalogs and wide-field survey databases have identified a small number of candidate systems with some Hoag-like properties. None of the published candidates matches the full combination of Hoag's properties simultaneously. The count of objects comparable to Hoag's object in all relevant respects, not just in visual appearance, remains very small after 7 decades of increasingly comprehensive survey coverage. The Sloan Digital Sky Survey represents the most relevant large-scale database for this search. Over its operational lifetime, the survey cataloged photometry and spectroscopy for hundreds of millions of astronomical objects, providing redshift measurements for tens of millions of galaxies across a significant fraction of the northern sky. Galaxy morphology classifiers applied to this catalog, including both human classification projects such as the Galaxy Zoo Citizen Science Initiative and automated machine learning pipelines, identified ring galaxy candidates within the dataset. The Galaxy Zoo project, which recruited hundreds of thousands of volunteers to classify galaxy images by morphology, found ring-like or ring-featured structures in a small fraction of all classified galaxies. Follow-up analysis of these candidates showed that a substantial portion were merging systems, galaxies with ring-shaped star-forming regions in their outer disks, or projection coincidences rather than true ring galaxies in the sense relevant to Hoag's object. After filtering for the relevant properties, the number of genuinely Hoag-like systems within the Sloan survey volume remains small. Machine learning approaches have extended the search capability without resolving the fundamental counting problem. Convolutional neural networks trained to classify galaxy morphologies can process millions of images in the time that human classifiers would require years, and their accuracy on common morphological types is high. Their performance on rare morphologies depends critically on how well the training data represents those morphologies. And for a class as rare as Hoag-like ring galaxies, training data is sparse. Networks trained predominantly on spirals, ellipticals, and irregular galaxies have no strong reason to develop accurate discriminators for a morphological class they encounter only a handful of times during training. The networks tend to absorb unusual morphologies into the nearest common category. A ring galaxy becomes an elliptical with unusual outer structure, or a face-on lenticular, or an unresolved compact system depending on distance, image quality, and the specific network architecture. Correcting for this systematic misclassification requires either training on augmented datasets that artificially oversample rare types or applying specialized classifiers built specifically for ring galaxy detection, both of which have been attempted and have expanded the candidate list without dramatically changing the estimated true frequency. Viewing angle introduces a correction that can be estimated quantitatively but not measured directly. A ring galaxy oriented so that we are looking through its disk plane rather than face-on across it does not look like a ring galaxy. It looks like two roughly parallel arcs of stellar light, or an elongated smudge depending on spatial resolution, or an irregular galaxy if the ring and core contribute comparable fluxes. The fraction of a population of ring galaxies that would be recognized as such in any given survey depends on the range of inclinations that produce a recognizable ring signature. For a thin ring with a sharply defined gap, face-on presentation makes the ring classification obvious. Edge-on presentation makes it nearly impossible. Intermediate inclinations produce a gradient of recognizability. Integrating over all possible viewing angles and applying the fraction that produce identifiable ring morphology gives a correction factor that can be applied to the observed frequency to estimate the true space density. Depending on the assumed ring geometry and the survey's classification sensitivity as a function of inclination, this correction factor ranges from a few to perhaps an order of magnitude. The true space density of ring galaxies is likely several times higher than the catalog frequency suggests. Even after applying this correction, the population of Hoag-like ring galaxies remains rare. Rarity itself is information, but the information it contains depends on what produces the rarity. There are two distinct possibilities with different physical implications. Rarity might reflect rare initial conditions within perfectly ordinary physics, a collision geometry so precisely configured that it occurs only once in some large number of galactic encounters, combined with a mass ratio and velocity dispersion that fall in a specific range that produces all of Hoag's properties simultaneously. Under this interpretation, Hoag's object is a genuine tail of distribution event, real but uncommon, requiring no physics outside the standard framework. The rarity is the expected consequence of narrow initial conditions within a well-understood mechanism. Alternatively, rarity might reflect a formation mechanism that itself operates only in specific environments or under conditions that are rare, not merely in a geometric sense, but in a physical one. If Hoag's object required a particular dark matter halo configuration that forms only in specific cosmological environments, or an AGN feedback event of a specific energy scale that occurs only in a fraction of galactic systems, or some combination of factors that jointly realize with very low probability, then the rarity tells us not just that the geometry was unusual, but that the physical environment was unusual in a way that standard models do not predict well. The rarity would then be evidence for missing physics rather than evidence for a rare draw from a well-understood distribution. Distinguishing between these two interpretations from the frequency data alone is not possible. Both produce the same observational outcome. Very few Hoag-like objects in any survey. The distinction requires knowing not just how many such objects exist, but why they are rare, which requires understanding the formation mechanism well enough to calculate the expected frequency from first principles. That calculation cannot be performed while the formation mechanism remains unresolved. The frequency of Hoag-like objects is therefore simultaneously the most straightforwardly measurable property of the problem and the one whose interpretation remains most circular. The rarity is a constraint on the formation mechanism, but interpreting the constraint requires knowing the mechanism. Several candidate Hoag-like objects beyond the original have been studied in detail in the published literature. Each has illuminated a different aspect of the problem. Some candidates have visible impactor galaxies at the right distance, establishing that they likely formed through collisions, but simultaneously demonstrating that a collision-formed ring does not typically produce Hoag's object-specific combination of gap emptiness and ring symmetry. Others have ring stellar populations that are somewhat older than Hoag's, showing the evolutionary progression toward the dispersed annular structures that differential rotation eventually produces. A few have gap regions with significantly more detectable material than Hoag's gap, suggesting that the gap evacuation is a process with variable completeness rather than a universal feature of ring galaxies.